Domain-specific language for data-driven design time analysis and result mappings for logic programs. Master's thesis of Sebastian Hahner at the Department of Informatics, Institute for Program Structures and Data Organization, IPD. Reviewer, Professor Dr. Ralf H. Reusner. Second Reviewer, Professor Dr. Anne Koziolek. Advisor, Stefan Seifermann. Second Advisor, Frederik Reiche. From January 15th to August 17th, 2020. Abstract. In today's connected world, exchanging data is essential to many business applications. With the increase in connectedness and the growing volume of data, ensuring security, privacy, and conformance to legal restriction becomes increasingly critical. In order to cope with these requirements early, design time data flow analysis have been proposed. By explicitly modeling data and their characteristics, the architectural model can be automatically tested against formulated data flow constraints. These verification approaches transform the modeled architecture into underlying formalisms such as logic programs. In order to enhance the expressiveness of constraints, they often have to be formulated in the underlying formalism as well. This requires architects to know about the formalism, the transformed architecture, and the verification environment. We aim to bridge this gap between the architectural domain and the underlying formalism, which occurs in constraint formulation. We propose a domain-specific language, DSL, which enables architects to define constraints while defining the architecture. By utilizing the terminology which is used to model the architecture, individualized constraints can be formulated without knowledge on the verification process. We provide a mapping of constraints formulated in our DSL from the architectural domain to the underlying formalism. Analysis results are mapped back into the architectural domain to ease their interpretation. The DSL is based on the generalization of existing constraints from real-world case studies. We evaluate the DSL's expressiveness, usability, and space efficiency for different sized data flow restrictions. Approximately 75% of examined constraints can be expressed using the first version of our DSL, while requiring up to 10 times less code. Besides the basics of data flow modeling and the modeling environment, no further knowledge on the transformation and verification mechanism is required. Additionally, we investigate the equivalence of analysis results of transformed constraints defined in our DSL with constraints formulated in the underlying formalism. In our tests, the transformed constraints achieve 100% recall while maintaining 90% precision. Zusammenfassung. In der vernetzten Welt von heute ist der Austausch von Daten für viele Anwendungen unerlässlich. Mit der zunehmenden Vernetzung und dem wachsenden Datenaufkommen wird die Gewährleistung von Sicherheit, Datenschutz und die Einhaltung rechtlicher Vorgaben immer wichtiger. Um diese Anforderungen frühzeitig gerecht zu werden, können Datenflussanalysen zur Entwurfszeit eingesetzt werden. Durch explizite Modellierung der Daten und ihrer Eigenschaften kann das Architekturmodell automatisch gegen Datenflussbeschränkungen getestet werden. Diese Verifikationsansätze transformieren die modellierte Architektur in ihnen zugrunde liegenden Formalismen, wie zum Beispiel logische Programme. Um die Aussagekraft der Beschränkungen zu erhöhen, müssen diese oft ebenfalls unter Nutzung der Formalismus ausgedrückt werden. Dies erfordert von Architekten Kenntnisse über den Formalismus, die transformierte Architektur und die Verifikationsumgebung. Unser Ziel ist es, die Lücke zwischen der architektonischen Domäne und dem zugrunde liegenden Formalismus zu schließen, die bei der Formulierung von Datenflussbeschränkungen auftritt. Wir schlagen eine domänenspezifische Sprache, DSL, vor, die es Architekten ermöglicht, Einschränkungen bereits während der Definition der Architektur festzulegen. Durch die Verwendung derselben Terminologie, die auch zur Modellierung der Architektur eingesetzt wird, können individualisierte Beschränkungen ohne Kenntnisse des Überprüfungsprozesses formuliert werden. Zusätzlich stellen wir eine Abbildung der in unserer DSL formulierten Einschränkungen von der Architekturdomäne in Formalismus vor. Analyseergebnisse werden in die Architekturdomäne zurück abgebildet, um deren Interpretation zu erleichtern. Die DSL basiert auf der Sammlung und Generalisierung bestehender Einschränkungen aus realen Fallstudien. Wir bewerten Aussagekraft, Nutzbarkeit und Kompaktheit der DSL für Datenflussbeschränkungen unterschiedlicher Größe. Ungefähr 75% der untersuchten Beschränkungen können mit der ersten Version unserer DSL ausgedrückt werden, wobei bis zu 10-mal weniger Quelltext benötigt wird. Neben den Grundlagen der Datenflussmodellierung und Wissen über die Modellierungsumgebung sind keine weiteren Kenntnisse über den Transformations- oder Verifikationsmechanismus erforderlich. Zusätzlich untersuchen wir die Äquivalenz der Analyseergebnisse von Beschränkungen, die in unserer DSL formuliert wurden, mit Beschränkungen, welche direkt unter Nutzung des Formalismus ausgedrückt wurden. In unseren Tests erreichen Beschränkungen, welche mit Hilfe unserer DSL formuliert wurden, eine 100%ige Ausbeute mit einer Präzision von 90%. To Alina, Beate und Markus. Chapter 1. Introduction. In today's connected world, exchanging data is vital for a lot of business applications. To ensure software quality attributes like performance and reliability, the fact of data processing has to be considered early in the design process. By only considering the confront flow of applications, some of these effects do not become visible. Data-driven analysis try to answer design questions by modeling the flow of data explicitly. Data-driven architecture description is especially helpful in terms of security and privacy reasoning because people usually talk about confidentiality in terms of data rather in terms of processes. To ensure properties such as confidentiality, the modeled data flow has to be analyzed. Automated data flow analysis are needed because detecting confidentiality issues manually is not feasible. The prerequisite of automated analysis are formalized architectural models. In order to aid the software architect, data-centric Palladio, an extension of the Palladio component model, has been proposed. Explicitly modeled architectures allow verification at design time through techniques like simulation, model checking, and theory proving. Data-centric Palladio uses the logic programming language Prolog to test model data flows against specified constraints. An example is the restriction of confidential data like personal user details to never leave a specified part of a system, for example an internal protected server. A transformation chain enables automatic verification by mapping the model architecture to executable Prolog code. After the execution, constraint violations indicate security issues and can be traced back. In order to define specific constraints on the system's behavior and flow of processed data, the constraints have to be explicitly expressed by an architect using Prolog. Here, multiple problems occur. First, it cannot be assumed that software architects know the underlying formalism well enough and are able to express constraint without additional training. Second, knowledge about the automatic transformation and the target meta model is required, since constraints are expressed against this meta model and the resulting code from the transformation. Third, the analysis results represented as Prolog solutions are not mapped back to the architectural model, which makes their interpretation more difficult. This gap between the architectural domain and the underlying formalism can also be observed in related work. With higher analysis variability, more knowledge about the underlying formalism is required. For instance, using logical formulas is more difficult than using previously defined metrics or annotations. In the following, we outline a contribution and give an overview of the thesis structure and content. 1.1 Contribution. We propose an approach to enable modeling of constraints using the terminology and abstraction of the architectural domain without the need of knowledge about the underlying formalism. We aim to define a domain-specific language, DSL, to express constraints and analysis goals at design time. Using this language, an architect shall be capable of defining generic or individualized data flow constraints for a modeled system without knowledge of the underlying formalism Prolog. Afterwards, our approach transforms the constraint into executable Prolog code, which checks whether the data restrictions hold for the modeled architecture. Last, possible constraint violations are transformed back into the architectural domain to ease the interpretation through the architect. Besides the engineering aspect of providing ready-to-use tooling, we answer the following research questions as part of this thesis. Which architecture level constructs and language elements are necessary in order to define data flow constraints? How is the mapping of constraints and results between architecture and formalism? We aim to minimize the risk of rebuilding the formalism in another domain without respect to real-world use cases. Thus, we collect case studies from related work to answer these questions. We focus on analysis goals in order to find a generalized approach to express data flow constraints. Additionally, we consider the analysis capabilities of underlying formalisms and its usage in data-centric Palladio as influential factor regarding the expressiveness of our domain-specific language. We present a list of requirements for such a language. To answer RQ1, we derive modeling concepts from these requirements and formalize them in a detailed meta-model in the architectural domain. Please note that it does not imply a feature-finished language with the same possibilities as Prolog, but rather an approach to enable the formulation of analysis goals for the majority of analyzed case studies. We answer RQ2 by extending the existing transformation approach from data-centric Palladio with a mapping from the newly defined domain-specific language to compliant Prolog code that reuses existing analysis capabilities. Additionally, we define mappings for the analysis results from the executed Prolog program back into the architectural domain. Please note that this step is not supposed to be equivalent to round-trip engineering as seen in the model synchronization because we expect different concepts in the analysis results than defined for the domain-specific language. 1.2 Outline. The remainder of this thesis is structured as follows. In Chapter 2, we discuss fundamentals like data flow modeling and domain-specific language. In Chapter 3, we present related work in the domain of transformation and analysis of architectural models. In Chapter 4, we summarize example scenarios using the remainder of this thesis. We discuss the integration of our approach in the existing analysis process of data-centric Palladio in Chapter 5. Afterwards, we collect language requirements in Chapter 6, which arise from case studies and the underlying formalism. We derive our domain-specific language syntax from these requirements in Chapter 7. Then, we discuss the language semantics, its transformation to Prolog code, and the mapping of results in Chapter 8. In Chapter 9, we evaluate our approach. We conclude with Chapter 10 and provide a short outlook on future work. Chapter 2 Foundations. In this chapter, we introduce fundamentals needed to explain this thesis. First, in section 2.1, we present the basic terminology used in data flow modeling. Then, in section 2.2, we briefly explain data-centric Palladio, an extension of the Palladio component model, to model and to analyze data flows. In section 2.3, we focus on domain-specific language, DSL. Last, the concept and terminology of logic programming is summarized in 2.4. 2.1 Data flow diagrams. A data flow diagram represents a system structure by modeling interfaces and data flows in between. The flow of control, for example one component calling another, is not in focus. DeMarco highlights that these diagrams present the workings of a system as seen by the data, not as seen by data processors, which helps from abstracting from individual operations. Data flows are often described using graphical notations. DeMarco provides rather informally semantics in natural language. The following conceptual elements can be used inside of data flow diagrams. Processes, represented by named circles. Data flows, represented by annotated arrows between processes. Files, represented by straight lines. Data source, represented by boxes with only outgoing data flows. And data sinks, represented by boxes with only incoming data flows. A flow of data starts at a source, for example a user's input, is processed in between and is terminated in a data sink, for example stored on a server. We visualize the simple scenario with exemplary process in figure 2.1. Here the input from the user is verified and then filtered using filter settings which originate from a file. Last, the filtered input is stored. The macro defines data flows as pipeline through which packets of information of known composition flow. This means that there is no upper limit of possible pipelines between two processes if data of different kind or with different purpose is sent. Through denoting multiple flows when applicable, the interfaces become more distinct. Data flow names shall represent what is known about data and its state, for example by differentiating user input and filtered input in figure 2.1. Naming data flow from files is optional, since file description is considered sufficient. Figure 2.1, simple data flow scenario of user input data processing. Process transformation incoming data flow into outgoing data flows. As discussed above, any number of incoming and outgoing data flows are valid. The macro defines files as temporary repository of data and thereby differentiates them from data sinks. Additionally, data sources or sinks are outside of the context of the modeled system. The store element in figure 2.1 is considered outside of a diagram's focus and thus modeled as sink. Otherwise, denoting it as file would be more accurate. Boxes in data flow diagrams can represent both a data source and a data sink simultaneously. Being outside the modeled system, data sources and sinks are not allowed to modify data. Only processes are allowed to transform data and are modeled explicitly inside the system boundaries. 2.2. Data-centric Palladio. Palladio is an approach to model software architectures and to predict quality attributes such as performance or reliability. The Palladio component model is a domain-specific language for specifying and documenting software architectural knowledge. Through analysis methods like simulation, complex software systems performance can be predicted early in the design process. To achieve this, we specify several information. We encapsulate component behavior in service effect specifications, SEFs, which are stored in the component repository model. We wire these components together using the system model. We describe in the component allocation model how the system is deployed on hardware. The hardware is defined in the execution environment model. Last, the usage model describes the user's behavior while interacting with the system. Combined, these 5 models allow the prediction of quality attributes like performance. To allow further analysis regarding software quality attributes like security or privacy, data-centric Palladio has been proposed by Seiferman et al. Based on a conventional software architecture model, data-driven constraints can be added by the architect through custom annotations. The meta-model of data-centric Palladio allows the specification of data flow description using data sources and sinks, characteristics, and processing operations. We explain data flow modeling with sources, sinks, and processes in section 2.1. Additionally, data and processes can hold characteristics. Characteristics are name-definite sets of values. These are used, for example, to express roles or access rights on data. The data flow analysis compares the characteristics of data and processes. Here, characteristics can be modeled explicitly by the architect or inferred implicitly. An example for this are data characteristics depending on the data source. Thus, characteristics of data may change when being processed in the system. We use processing operations to express the transformation of data flows from source to sink. Examples are data filtering or aggregation. To exchange data between components, we define data transmissions. Figure 2.2, Ceph with data flow annotation. Using the meta model of data-centric Palladio, Palladio Cephs can be annotated with data flow information as shown in figure 2.2. All specified data and processes can hold characteristics. The action get flight offers is described using a data flow from the flight offer store to the user. Based on the requested data, results are processed, selection. After modeling data flows, we can evaluate specified constraints automatically. For this analysis, the model is transformed into executable Prolog code. The output of the program provides insights whether or not the model architecture holds the specified requirements. 2.3. Domain-specific languages. Several definitions of domain-specific language can be found in other work. Van Duysen and others define them as follows. A domain-specific language, DSL, is a programming language or executable specification language that offers, through appropriate notations and abstractions, expressive power focused on and usually restricted to a particular problem domain. This definition holds multiple aspects of DSLs we want to briefly discuss in the following. DSLs offer appropriate notations for end users and are also called end-user programming. Thus, the end user needs no in-depth knowledge of formalism and only needs to understand the DSL to be more capable of handling more complex tasks. This can have a positive impact on the user's productivity. Other opportunities of DSLs are self-documentation through meaningful notations, consistency, proper level of abstraction, and enhanced maintainability. Use cases are analysis, verification, and optimization. In comparison, a general-purpose language, GPL, offers a more generic approach. A DSL offers appropriate domain-specific notations from the start. Additionally, GPLs tend to require more boilerplate code. Conciseness shall be considered throughout development in order to avoid accidental complexity. DSLs don't have to be directly executed and can rather be transformed into an executable representation. To create a DSL, domain-specific knowledge has to be combined with language development skills, which is considered hard. In the following, we present Plant UML, an example for a DSL which shows both the enhanced intuitiveness and restrictiveness to a defined domain. Plant UML is an open-source DSL to textually define UML diagrams. Figure 2.3 shows a simple class diagram modeling the simplified relation of an object and an array list. We show the textual representation in listing 2.1. Even without seeing the diagram, Plant UML code can be understood due to its intuitiveness. However, this is not the case for all textual representations of UML diagrams. For example, XML is worse readable. Figure 2.3, a simple class diagram. Listing 2.1, Plant UML DSL code of a simple class diagram. 2.4. Logic programming. Logic programs follow a different paradigm than classical procedural programming languages like Java or C++. The procedural paradigm consists of statements which are executed from start to end. These can be encapsulated inside control structures like conditional constructs or loops. In comparison, logic programs follow the declarative paradigm. They consist of facts and rules which can be combined and solved by the programming environment. The programmer does not specify how to solve the program. A well-known logic programming language is Prolog, which stands for Programming in Logic. Using the Prolog environment, questions, called queries, can be asked to previously defined system of facts and rules. We provide a short example based on Prama et al. In listing 2.2. The first two lines are facts which declare that Fido and Henry are dogs. The third line is a rule specifying that anything can be called an animal if it's a dog, or in more natural language, all dogs are animals. Listing 2.2, simple prologue example with facts and rules. With this simple set of facts and rules, some first questions can be asked. To answer these, the prologue environment solves the underlying logic program. We show queries and their results in listing 2.3. The first query is straightforward. We ask if Fido is a dog. Because of the first fact in listing 2.2, this evaluates to true. The second query asks if Fido is an animal. Because of our rule in the last line of listing 2.2, this is also true. In the last query, we ask if there can be found any facts about dogs which evaluate to true. This is the case for both Fido and Henry. Based on the building blocks, complex logical relations can be formalized and solved. A detailed description how Prolog approached such problems using unification and backtracking can be found in Source 3, Chapter 3. Listing 2.3, simple Prolog queries and results. In order to expand this basic understanding of the Prolog environment, we summarize important language elements and terminology. Terms are a basic building block of Prolog programs. By adding arguments, they become compound terms. The number of arguments is specified by their arity. The next bigger building block is the clause, also called sentence or rule. It consists of a head and a body. The head represents the identity of the rule and can be expressed using an atom, a textual constant, or a compound term with arguments. The body itself is a clause and thus a term. The semantics are straightforward. The body implicates the head. In line 3 of listing 2.2 we see such a rule. The head and body are built up from compound terms with one argument and thus with the arity of 1. Facts are clauses without body. Thus they have no condition which must be satisfied. In listing 2.2 we can see such facts for Fido and Henry. A predicate represents a collection of clauses with the same functor, which means matching name and arity, like dog. A Prolog program is a collection of predicates. After defining the program, the Prolog engine can answer questions called goals or queries as shown in listing 2.3. If a goal succeeds, a solution with bound variables is returned. The query fails if Prolog is unable to find a solution which satisfies the question. Chapter 3. Related work. In this chapter we give an overview of related work for this thesis. The common research field of all related work is the design time analysis of software architectures. Related work discusses the use of different formalisms to analyze software quality attributes like performance or to ensure security. In order to perform such analysis, these approaches transform the formalism which allow automated verification. This includes approaches based on the Palladio component model in section 3.1, security modeling approaches like UML-SEC and software architecture models in section 3.2, and data flow-oriented approaches like secure data flow diagrams and iFlow in section 3.3. We close with a short comparison of related work and our approach in section 3.4. 3.1 Alternative analysis for PCM. The Palladio component model is a DSL to document and evaluate software quality attributes like performance and reliability, please see section 2.2 for fundamentals. To analyze these models, different approaches were proposed. We summarized the analysis using layered queuing networks, LQN, and queuing P-tree nets, QPN. Both approaches use metrics which limit the expression possibilities of analysis goals of an architect. Koziolek et al. And others present a model transformation from the Palladio component model to layered queuing networks. They propose an automated model transformation from the architectural layer to a connected LQN solver. Their goal is to create a reusable transformation approach with performance advantage over discrete time simulation. The transformation is based on a defined mapping between PCM and LQN. The model is serialized afterwards and sent to the LQN solver for performance analysis. Users can change parameters of the architecture to quickly evaluate their influence on performance attributes. A limitation of their approach is the lack of solver feedback. Thus, analysis results are not processed but rather printed to the screen and have to be interpreted manually by the architect. Maya and others propose an automated transformation of component-based software architecture models to queuing P-tree nets. They use a model-to-model transformation from PCM to lower-level QPNs and simulate the model system afterwards. The mapping is provided using QVTO. To enable user input and specification of desired analysis results, instrumentation UI and instrumentation model is defined. Together with the result integration, this approach lets the user view simulation results and identify performance problems without leaving the architectural abstraction level. The user can define the level of detail of desired results from simple aggregations to detailed histograms. This influences the amount of collected data and the simulation time. Although the results are mapped back to architectural domain, they are only printed to the console and to a results file without further processing. 3.2 Security Modeling. The field of model-driven security tries to solve security-related questions at design time using model-driven approaches. Through early modeling of critical system aspects, costly changes in later steps of the software development process can be avoided. These approaches are related to our work because they also handle transformations from the architectural domain and analysis goal specification. We present the modeling approaches Software Architecture Model, SAM, and UML-SAC. They have already been discussed in previous work. UNT and others propose the usage of software architecture models for security analysis of distributed systems and as formal basis for analyzing software architecture specifications. SAM is based on a dual formalism consisting of P-tree nets and temporal logic. The approach allows hierarchical decomposition of software architectures and verifying constraints automatically using model checking or theorem proving. To analyze and formalize architecture, it is transformed into a finite state system. User input constraints formalized in linear temporal logic, LTL, are transformed into computational tree logic, CTL. The analysis returns whether the constraints hold for the given system. If not, the failure is demonstrated by an execution sequence. This approach offers a higher analysis variability compared to other related work. Still, the architect has to use the formalism LTL to specify constraints. Juyens and others present the UML-SAC approach, which extends the Unified Modeling Language (UML) with security engineering-related techniques. Through the usage of stereotypes and constraints, UML diagrams can be annotated with security attributes, for example by defining data as confidential. To verify model systems, a transformation into abstract state machines is provided. These can be model-checked against an adversary using SPIN and the Promela language. The adversary's behavior is based on the previously annotated diagrams. If a vulnerability has been found, a trail file which records the sequence of actions of the potential attack, is produced. This file is handed over to the error analyzer, which creates a report containing the problems found. Through this transformation, the architect can model the system security and view the analysis results on the same abstraction level. However, Jürgen states that there is still a lack of feedback from the model checker back into the UML model, which makes the result interpretation more difficult. Chapter 3.3 Data Flow-Oriented Modeling. In this section, we summarize related work providing approaches for data flow-oriented analysis. This includes security data flow diagrams and iFlow. Please note that these approaches could also be considered as security modeling, see section 3.2. We chose to list them separately because of their strong relation to data flow-oriented analysis. Both approaches use annotations which limit the architecture analysis capabilities compared to a DSL. Pelzus and Anders present secure data flow compliance checks between models and code based on automated mappings. The mapping is created semi-automatically through combining design-level SecDFD models with corresponding implementation. SecDFD is a graphical representation of data flow diagrams extended by security annotations. Their goal is to aid architects by discovering secure data flow compliance violations. Pelzus and others state the importance of tool assistance because manually mappings are inefficient and error-prone. They propose a semi-automated mapping between model and code based on heuristics like matching structures and signatures. The user has to verify these mappings afterwards in an iterative process. The final mapping can be used for compliance checks, for example, by applying security metrics. The verification of model data flow contracts without the help of external analysis tools is considered future work. Katgalov and others propose the model-driven development of information flow secure systems with iFlow. iFlow provides an environment for modeling of flow-sensitive applications. These models can be used to automatically generate deployable app and web service code as well as formal model. Based on an annotated UML diagram, restrictions can be formally verified. Therefore, the model is transformed into an abstract state machine and used as input for theory proving. Proved goals are generated automatically based on security-level annotations by the user, for example, which data is considered to be kept private. The proving step yields whether the rules of non-inference hold for the specified system and restrictions. It's not discussed if there is any other processing of the analysis results. 3.4 Comparison. To conclude, we compare the different approaches listed before. We focus on aspects which are relevant in the scope of this thesis. This includes the user's influence on the analysis goals and their domain of definition, the analysis method, and the processing of results. The comparison is summarized in Table 3.1. All approaches have the common goal to aid the architect on design decisions by analyzing architectural models. First, we discuss the domain of analysis goals. Possible domains are the architectural domain if no knowledge is required about the underlying formalism. Except for SAM, all approaches use the architectural domain to formulate analysis goals. The variability of requirements, constraints, or analysis goals depends on the provided formalization. Related work uses metrics, logical statements, or annotations for modeled software systems. We consider the selection of metrics having a lower analysis variability than annotating models. Using the underlying formalism, or a DSL, is supposed to have the highest variability. A common gap is mapping of analysis results. Only UMLSec and Palladio QPN offer a transformation of analysis output back into the architectural domain. Still, this mapping is limited and does not allow result interpretation in the same view which has been used for modeling. Table 3.1, comparison of related work. We added a comparison to the current state of data-centric Palladio as well as the aspired goals of this thesis. Data-centric Palladio relies on the formulation of constraints using a formalism in addition to annotating the architectural model. Thus, we consider it having high analysis variability. The goal of this work is to enable the architect to define constraints in the architectural domain using a DSL instead of the formalism. Additionally, we use result mapping to transform analysis results back into the architectural domain, which eases the interpretation of constraint violations. Chapter 4. Example scenarios. In this chapter, we introduce two example scenarios. These scenarios are used for the requirements analysis, the language design, RQ1, and the mapping to the underlying formalism, RQ2. Both scenarios originate from other work in the field of design time analysis. 4.1. Geolocation constraints. This example scenario is based on work by Seiferman and others, Kunz and Weimann. It has been previously used to develop parts of the transformation of data-centric Palladio. We simplify the scenario to clearly show the usage of characteristics for data flow analysis. The scenario is based on geolocation restrictions implied, for example, from the government. An example are the General Data Protection Regulations (GDPR), which do only allow personal data to be processed or stored within the European Union or certain countries with equivalent privacy regulations. Thus, this example represents a data flow restriction based on the kind of data and processing location. We define the characteristics of this scenario as follows. Privacy level, either personal or anonymous. Data is considered to be personal if it can be associated with a person, for example, name, address, phone number. Otherwise, it is considered to be anonymous, for example, product lists, stock quantities, or item descriptions. Location. In this example scenario, either EU, USA, or Asia. Thus, a place can be inside the EU or not. As mentioned previously, personal data shall be protected in conformance to legal restrictions. Personal data with its origin inside the EU is not allowed to be processed in a non-EU location. In order to implement this scenario using data-centric Palladio, we used the data's privacy level, personal or anonymous, and the location of a service, EU, USA, or Asia, as characteristics. We annotate a model system with these characteristics. A common instance of this scenario are international online shops, which have to synchronize shop information across borders but are not allowed to do so with personal data. In figure 4.1, we show the diagram of a simple online shop. The shop server contains the web store component, which is used to view and buy products. If the user views products, the web store calls a recommender to get additional information and products to show to the user while browsing. This component is deployed on a separate recommendation system. When the user buys a product, its personal data is stored in a database, which is deployed on a database server. Figure 4.1, deployment diagram of the geolocation constraints example scenario. We annotate all servers with the location characteristic, which represents the location of their deployment, and we annotate all user endpoints with the privacy level characteristics. Trivially, USA and Asia are non-EU locations. With this information, we can test if the constraint "no personal information is processed outside of the EU" holds for every data flow. In the example shown in Figure 4.1, the data flow from the user to the web store to the recommender fulfills this constraint. Although the recommender is displayed with the recommendation system in the USA, a non-EU location, only anonymous data is processed, which is excluded from the restriction. This is not the case for the buy products data flow. Personal information flows through the web store first, which is no problem since it is located inside the EU. However, storing the data in the user's database violates the constraints since the database server is located in Asia. Please note that this example represents a very basic scenario. Still, it's prototypical for real-world problems regarding legal regulations, and one can simply imagine that complex international online shops cannot be checked against data flow constraints by hand without tool support. 4.2 Access Control. This scenario represents another popular use case of data flow restrictions. Access control systems manage security by assigning access rights to sensitive information. Prior to allowing data access of actors, the system checks their authorization. A well-known example of this behavior is the Unix file system. The data flow constraint of access control systems can be formulated as follows. Data access is only permitted if the actor's role is authorized. We model this behavior using the actor's roles and the data access rights as characteristics. Every datum has a defined list of authorized roles. A constraint violation occurs if an actor gets access to a datum which does not have the actor's role in its authorized role list. We illustrate this in Table 4.1 using 4 simple roles. In theory, this represents a test for emptiness of the intersection of 2 sets. Table 4.1 Constraint violation example in access control systems. Table 4.2 Actors and roles in the travel planner example. We consider a simplified version of this travel planner case study which has been previously used in other work. In this case study, users install a travel planning application on their smartphone. They have a credit card center app installed which manages their credit card details. The travel planner app is sponsored and developed by a travel agency that acts as a broker for the airline. Typical usage scenarios are requesting flight offers and booking flights. Since the latter requires the exchange of sensitive information, we model the roles explicitly in Table 4.2. Possible roles are user, travel agency, and airline. Both the travel agency and the airline have their corresponding roles. The travel planner app and the credit card center app have the role user, since both are installed on the user's smartphone. We show the deployment diagram of the simplified scenario with according role annotations in Figure 4.2 and a sequence diagram in Figure 4.3. In the following, we discuss the occurring data flows and the access rights of exchanged data. First, the user requests flight offers using the travel planner app. The app forwards the request to the travel agency, which forwards it again to the airline. The list of all flights offers is then sent back through the travel agency to the travel planner app and displayed to the user. All exchanged data, the flight offer request and the resulting offer, authorize all existing roles, user, travel agency, and airline. Trivially, no constraint violation occurs. The user chooses a flight offer and initializes the booking process through the travel planner app. This time, the request is sent directly to the airline. Thus, the datum holding the selected flight only authorizes the roles user and airline. A constraint violation would occur if information about a selected flight would flow to the travel agency. Additionally, the travel planner app transmits credit card data to the airline. Initially, this data is only authorizes the role user since it's considered sensitive. In order to be passed to the airline, it has to be declassified using the credit card center app, which includes a permission request shown to the user. By accepting this request, the role airline is added to the credit card data. This allows the airline to access selected information about the credit card without a constraint violation. Figure 4.2, deployment diagram of the travel planner example. In comparison with the geolocation constraint scenario shown in section 4.1, this data flow analysis requires additional effort. The characteristics of data which flows from the credit card center app are not fixed but rather depend on the user input. Additionally, characteristics are represented by sets instead of single values. Figure 4.3, sequence diagram of the travel planner example. Supporting the existing analysis process, Chapter 5. In this chapter, we discuss the integration of our approach into the existing development process of data-centric Palladio proposed by Seiferman and others. As discussed in Chapter 1, the status quo suffers from multiple problems. There is no abstraction enabling the architect to define analysis goals without knowledge of the underlying formalism and the representation of the transformed architecture model. Analysis results are also affected by this domain gap. We propose the usage of a domain-specific language DSL to bridge this gap and inspect high-level constructs RQ1 and their mapping to Prolog RQ2. Figure 5.1 shows the extended development process. White elements represent existing process elements, while gray elements are part of a contribution. Elements with dashed borders annotated with gear icons are hereby fully automated without user interference. All other activities are performed by the architect. The starting point of data-centric Palladio is a software architecture description based on the Palladio component model, which does not consider data and is processing explicitly. In order to enable the analysis of data flows, the architects define data and its processing explicitly. In order to do that, he defines the characteristics and annotates the existing software architecture model. These characteristics represent, for example, the sensitivity of data as shown in section 4.1. For more information on the usage of data-centric Palladio, please refer to section 2.2. After the data flows under consideration are defined, data-centric Palladio transforms the model and its annotations to the operation model. This intermediate step is proposed because it decouples the analysis from the ADL, architectural description language, and used to model the system. The operation model is a simplified analysis model consisting of operations and their processing of data. Afterwards, the generated model is transformed to executable Prolog code. Both steps can be executed automatically. The definition of analysis goals is independent from the transformation. The architect uses our proposed DSL to define data flow constraints. He defines restrictions based on the characteristics from the previous step. An exemplary constraint from section 4.1 is the restriction of sensitive user data to not flow to the specified location. Afterwards, the formulated constraint is transformed to executable Prolog code and combined with the previously generated code from the operation model. The result of this step is a Prolog program, which is used to find data flow issues by evaluating every defined constraint. The result of this analysis is a list of violations which refer to the operation model. In order to aid the architect, these violations are mapped back into the architectural domain. This enables the architect to interpret the results in the last step without the need to leave his domain or her domain. All steps from the transformation of the DSL to Prolog to the architecture analysis and the result mapping are automated. Figure 5.1, extended development process with data-centric Palladio. Data-centric Palladio favors an iterative approach. If the modeled architecture does not meet all requirements, it can be adjusted based on the analysis results. Previously defined data flow constraints can also be changed or refined after each execution. Chapter 6. Language requirements. In this chapter, we collect requirements for the language design. In order to discuss which constructs and high-level elements are necessary for our DSL, RQ1, we consider two influential factors. First, we show case studies and analysis approaches from the security modeling domain. Please see section 3.2 in section 6.1. Then we summarize the existing analysis approach from data-centric Palladio, which uses Prolog and the constraint query API from Kurze in section 6.2. This method is motivated by the feature-oriented domain analysis FODA, which supports reuse at the functional and architectural levels. They identify four major factors which influence a generic domain model: the capabilities from the end user's perspective, the applications of environment, the domain technology, and the implementation techniques. These can be summarized as user-centered, top-down, and technology-centered, bottom-up. Thus, we both generalize existing case studies, top-down, and abstract from existing constraints formulated in the underlying formalism, bottom-up. The results from the case studies can be interpreted as lower limit of requirements which the language has to satisfy in order to define applicable data flow constraints. The underlying formalism, namely the constraint query API, is the upper limit of functionality, since we cannot define any constraint which is not translatable into it. Trivially, using Prolog without our DSL represents the upper limit but lacks the desired abstraction. Kluge Aussage. 6.1. Case studies. We collect data flow scenarios from case studies and analysis approaches from other work in the security modeling domain. The studies have already been used in previous data-centric Palladio related work from Kurze. We extract information about data flows and their case-related restrictions. Then we show similarities and generalize the constraint requirements. This represents the lower limit of language requirements. The geolocation scenario was used in previous work from Kurze and Weimann. It describes data flow restrictions which originate from the legal framework of international online travel. We describe a simplified version of this scenario in section 4.1, which only divides the sensitivity of data in fully sensitive and fully anonymous without finite gradations. The restriction of data flows rather depends on the processing and the environment. We repeat the definition of free confidentiality levels from the work of Weimann. Type 0 personal information. Data which is directly related to personal information, for example name, address or credit card number. Type 1 personal identifiable information. Data which does not directly contain personal information. If this data is combined with other type 0 or type 1 data, personal information can be reconstructed. Type 2 anonymous data. Data which does not reveal any personal information, even combined with other data. Hier fehlt ein Punkt. In the following, we discuss the constraint formulation. The simplified scenario shown in section 4.1 focuses on type 0 and type 2 data. As type 2 does not hold any personal information, its data flows are not restricted. Type 0 data holds sensitive information and thus always needs to be protected. We only allow the processing of type 0 data flows in safe locations. In the context of a legal framework, this is, for example, the same country that the data originates from. In section 4.1, we describe the constraint as no personal information is processed outside of the EU. By using confidentiality levels, this can be generalized to no type 0 information is allowed to flow outside of a safe location. Here, the term flow implicitly covers processing or storing of data. Please note that we do not define safe locations here, but rather leave this to the concrete analysis. The restrictions on type 1 needs further information about the context of data processing. Here, the joining of two different data flows from different sources has to be prohibited because this would enable the retrieval of personal identifiable information. Kunz models the source of data as data type for illustration purposes. However, he points out that an alternative would be the use, da fehlt ein Wort, would be, to use, auch dann fehlt ein Wort, be use of an additional attribute to the data which specifies the information source. In order to prevent the joining of data flows, the constraint can be formulated as follows. No type 1 data is allowed to flow to a location where other type 1 data is processed if both have different data types. This first scenario reveals multiple requirements for formulating data flow constraints and thus language elements. We collect our findings in the following. R1. Constraints restrict the flow of data between sources, processes, and sinks. Please see section 2.1 for details on the terminology. They abstract from the concrete processing, operation, parameters, and control flow. Data can be selected by its characteristics, R2, for example, type 0 data. R3, data can be selected by its data type. R4, groups of processes and sinks can be selected by their characteristics, for example, the location. R5, processes and sinks can be selected by their identity, for example, restricting multiple data flows from being handled in one process. R6, characteristic selection can be inverted, for example, every location except the EU. R7, characteristic selection accepts multiple values, for example, Asia and USA. R8, multiple forms of a characteristic can be combined to named classes, for example, safe locations. R9, multiple data flows can be considered in one constraint. For example, two distinct Type 1 data flows. Ich will gerade mal kurz hier über diese Aussage nachdenken. Das hier. Verliert man hier viel Ausdrucksmächtigkeit? Das ist ein Fluss als Speichern und Process? Wahrscheinlich ist es egal für unsere Abstraktionsebene. Ja, spannend. The Travel Planner case study originates from the iFlow project. It represents an access control system. This system only permits an actor to gain access if the requested datum is open for the actor's role. A simple example are system critical files of an operating system. A system administrator is allowed to access these files while normal users are not. The actor's roles and the authorized roles of a datum can be both modeled using characteristics. The Travel Planner case study represents a typical scenario of planning a travel by plane. We explained this case study in detail in section 4.2. The involved actors are the user, a travel agency, and an airline. The user books a flight offer and transmits credit cards details, which is considered to be sensitive. Thus, only the airline is permitted to gain access after the user explicitly declassified the information. This can be explicitly modeled by controlling the roles which are allowed to gain access on credit card data. The list of roles is not static but changes over time, for example when the data is declassified and sent to the airline. Other information, such as data about flight offers, is not restricted at all and can be viewed by all actors. This case study represents only one case of the usage of access control systems. In order to define a generalized constraint, we do not consider example data, for example credit card data, but rather restrict the data access using the characteristics actors' roles and authorized roles. Both characteristics are modeled using sets rather than single values. If a datum's list of authorized roles does not contain at least one of the accessing actors' roles, a constraint violation occurs. There is no differentiation if an actor actively asks for the datum, in the sense of a call in the control flow, or if the datum passively flows to the actor, like in the example presented above. We define the constraint as follows. Information is only allowed to flow to an actor if the intersection of its authorized roles and the actor's roles is not empty. Intuitively, a non-empty intersection of both sets implicates that the authorized roles contains at least one of the actor's roles. We prefer the set operation since it can be used in a broader context. The analysis of this case study reveals additional requirements. We extend our list as follows. R10. Characteristics can be variable, for example an authorized role, and thus require further restrictions. R11. Variable characteristics can be represented by single values or sets, for example as single or multiple roles. And R12. Variable characteristics can be analyzed using set operations, for example the intersection of two sets or a test for emptiness of a set. Formal software architecture models SAM are related work to this thesis. Hugh and others represent another exemplary travel planner to explain their use of formalisms for defining requirement specifications. Please see section 3.2 for more information. The travel planner receives travel information and then books an appropriate flight, reserves a hotel room, and rents a car. The flight ticket is bought from Delta Airlines if the offer is lower than $400. Otherwise, the ticket is purchased at Continental Airlines. This internal decision is a critical point of the system. If the agent, which returns ticket prices for Delta Airlines, gains knowledge about the $400 threshold, it could always return $399. This would ensure that they always sell their own ticket while still maximizing their profit per ticket. To avoid this problem, they defined the following constraint, simplified. An agent's decisive data is not allowed to be leaked to another agent. Here, decisive data can be an arbitrary combination of input data, for example the price, user information, selected room or travel route or travel time. In the example above, the ticket price represents decisive data. The sensitivity of data has to be labeled for every agent. This constraint introduces one additional requirement, R14, 13. Data and processes can be selected by combining the selection of multiple characteristics. In the following, we summarize the findings from this section. Our goal is to define a lower limit of functional requirements for the language design. Besides defining language elements which seek to find similarities and a common constraint shape, we start by enumerating the previously defined determined data flow constraints. No type 0 information is allowed to flow outside of a safe location. No type 1 data is allowed to flow to a location where other type 1 data is processed if both have different data types. Information is only allowed to flow to an actor if the intersection of the authorized roles and the actor's roles is not empty. An agent's decisive data is not allowed to be leaked to another agent. Despite the fact that these constraints originate from different case studies and are related work, they show several similarities. First, they restrict the flow of data by not allowing it or only allowing it under certain circumstances, R1. The modality of this restriction is fixed, never allowing a data flow or leakage. Second, these restrictions only apply for selected cases and not for all data flows. Examples are 1. Only considering type 0 information, or 4. Only restricting decisive data. There is no information on data which does not fit a selection. In the geolocation scenario, type 2 data is allowed to flow to any safe or unsafe location. The data flow constraints follow a blacklisting approach. Data is selected based on its characteristics, R2, or attributes like data type, R3. The selection can also be inverted, R6, or combined with other characteristics, R13. Multiple values as R7 and classes of characteristics, R8, are also possible, for example, all safe locations. In some cases, the static value of a characteristic is not relevant, but rather its value in comparison with other data characteristics, for example in 3, which requires more detailed restrictions, R10 and R11. Besides the selection of data based on its characteristics, nodes like processes and things are selected. These are sometimes also called entities, actors, agents, or locations. Nodes are selected by their characteristics, R4, or by their identity, R5. The restriction of data flows in 2 and 3 is coupled on additional condition. This condition uses previously defined characteristic variables and evaluates them, for example, by testing for distinct sets in 3. Other variable comparisons and set operations are imaginable, R12. All constraints consider one data flow at a time for 2, which restricts the joining of distinct data flowing from multiple sources, R9. 6.2. Underlying formalism. In order to discuss the upper limit of functionality, we summarize the operation model and the constraint query API, which are used by data-centric Palladio. Because we extend this approach, please see chapter 5 for details. The analysis capabilities of this underlying formalism represent the upper limit of possible constraints. Last, we discuss abstraction possibilities and gaps between the architectural domain and the analysis domain. The operation model is used to intermediate model between the architectural description of a system and lower-level Prolog code. It can be seen as simplified analysis model. The transformation between the modeled architecture, the operation model, and Prolog code are fully automated. Because a proposed DSL is also transformed into Prolog code, which refers to this model, it's viable to consider it early in the design process. In the following, we show important elements from the operation model. Operations are central structural elements and represent processes which manipulate data, for example, a database store operation. Call parameters and return values are used to exchange data between operations, sources, and things, for example, the data to store in a database. State variables represent globally accessible data, which can also be used by operations. Properties represent characteristics of an operation, source, or sink. Properties are static and set in the transformation, for example, the location of a database. Attributes represent characteristics of data flowing between operations. Attributes are dynamic and can be manipulated from operations, for example, the sensitivity of data. Value set types are containers for characteristic values or literals. Both properties and attributes refer to these types, for example, the characteristics, location, and sensitivity. The operation model does not work with single data instances, but rather classes of data with matching characteristics. Data-centric Palladio doesn't specify the flow of data instances either. The use of characteristics to select classes of data is in focus. Characteristics are named finite sets of values represented by value set types and used in properties or attributes. This distinction is due to the semantic difference between constant operation characteristics and variable data characteristics. Every entry of a value set type is represented as Boolean value. For example, setting a data's privacy characteristic to private results in the data type's attribute privacy private set to true. Using the constraint query API, the system can then be queried for constraint violation. Prior to the development of our DSL, this was the proposed way of interacting with the operation model. We summarize the predicates which are provided by the API. For a full reference, please refer to reference 25, page 41. Listing 6.1 shows basic predicates of the API which can be used to bind typing information. This can be seen as first step to more complex queries for which one would normally use the universal or the existential quantas. Line 1 to 3 shows predicates for the names of atomic building elements, namely properties, attributes, and operations. Using the predicates from line 5 to 7, we can combine this information to ask if a named value, attribute, or property belongs to a value set type. With the predicates from line 9 to 11, the relation of operations with parameters, return values, and state variables can be queried. Listing 6.1, basic predators of the constraint query API. Based on this information, we can use more advanced predicates which query the flow of data and their characteristics. We summarize these predicates in listing 6.2. The operation model uses a stack to represent the control flow through the system. Every operation, each call is put onto this stack. The most upper element is always the current operation under consideration. The most lower element of a correct call stack is the system usage, which can be seen as entry point to any valid call sequence. The predicate stack valid checks if an arbitrary list represents such a correct call stack. The predicates in line 3 and 4 are used to determine if an operation has a property or a property with a given value. As stated before, properties represent characteristics of processes in a data flow. For example, has property OP location evaluates to true for every operation if the location would be modeled for all operations. Listing 6.2, advanced predicates of the constraint query API. Characteristics of data flowing through the system in the form of parameters and return values are modeled using attributes. The predicates from line 7 and 9 are used to check if the operation on the top of the call stack has call parameters and return values with their attributes set to the requested value. Is, for example, the sensitivity characteristics of data modeled explicitly, every ingoing parameter and outgoing return value of any operation in the call stack can be tested for sensitivity. This is also the case for state variables. Since state variables have to be unambiguously identified, the containing operation which uses the variable must also be specified in order to use the predicates from line 12 to 15. The choice of predicate pre or post determines if the variable is considered before or after operation call. In order to discuss both lower and upper limits, we combine the findings from this section with the discussion on higher level language requirements from the previous section. The comparison of interaction with the constraint query API and the way we formulated constraints in section 6.1 shows multiple domain gaps which have to be resolved. First, a gap in the representation of model elements exists. All constraints refer to architectural model elements, for example components, or higher-level entities, for example agents or actors. In the context of data flow modeling, these are represented by sources, processes, or sinks. Please see section 2.1. These elements are selected by characteristics R4 or their identity R5. Fortunately, the existing transformation of data-centric Palladio transforms these elements from the architectural domain to the operation model while retaining their characteristics or properties in the terminology of the operation model. This is also the case when speaking about data. All constraints select data, for example, by their characteristics R2 or meta-attributes R3. Also, multiple characteristics R13 or characteristics with multiple accepted values R7 are possible. The transformation to the operation model transforms characteristics to value set types. Using predicates like call argument and return value, this information can be queried. Combinations of multiple characteristics or values are also possible using Prolog built-in predicates to combine multiple terms. Some constraints require additional conditions, R10, 11, and 12. For example, comparing two sets of roles for access control systems. The realization of these constraints using the Constraint Query API requires additional steps, for example, introducing new variables and evaluating them separately. This can also be achieved using Prolog. Besides selecting data and processes, all constraints show a similar structure. They restrict the flow of data to, for example, never allowing it to, under certain circumstances, R1. Constraints following the approach can be expressed by using the predicates from the Constraint Query API shown in this chapter and bridging the domain gaps discussed before. We select data, parameters, return values, and state variables and operations from the call stack. The execution of the formulated query then returns violations which match our selection. Chapter 7, Language Syntax. In this chapter, we present the syntax of our domain-specific language DSL. RQ1 asks which elements are necessary to define data flow constraints. We discuss architecture-level constructs and language elements which are used to satisfy these requirements discussed in Chapter 6. We start by giving a brief conceptual overview of the DSL in Section 7.1. In Section 7.2 to Section 7.4, we discuss the language elements in detail and show their relation to the previously collected requirements. Last, we formulate constraints for the example scenarios shown in Chapter 4 and explain the usage of the DSL in Section 7.6. We focus on the abstract syntax of our DSL, which is represented by the language metamodel. Our contribution to RQ1 is the analysis of domain elements rather than their concrete representation. Furthermore, Furthermore, an abstract syntax can be represented by multiple concrete syntaxes. We show our concrete syntax at the end of each section, but refer to it as an exemplary concrete syntax. (7.1) Overview. The purpose of our DSL is to define constraints which restrict the data flow. In order to aid the architect to reason about these data flows, we only use concepts from the architectural domain. In Section 6.1, we discuss that all analyzed constraints follow a common pattern. They restrict the flow of selected data without considering the control flow, R1. They use the modality of never allowing a data flow. Furthermore, conditions can be used to precisely specify forbidden behavior. In Figure 7.1, we show the simplified abstract syntax of constraints in our DSL. We annotate the elements with notes to show how the syntax parts relate to the exemplary constraints from Section 4.1. No personal information is processed outside of the EU. Please note that this is only a simplification. For the complete metamodel, refer to Section A4. A constraint is a named entity defined by the architect. Each constraint contains a rule which defines the desired restriction of data flows. The statement sets the modality of the rule. As discussed before, all constraints gathered in Section 6.1 require a data flow to never flow under certain circumstances. A constraint only subjects selected data and selected destinations. The selection step is required because restricting all data flows without limitation is not considered to return viable results. Thus, data selector and destination selector are obligatory elements for each rule. We include multiple ways to select data and destinations. First, they can be selected using characteristics which have been introduced by data-centric Palladio. Our DSL is integrated into the analysis process and references characteristics on previously defined architectural models. For more information on the complete process, see Chapter 5. A characteristic selection can be used both as data selector and destination selector. In case of the geolocation constraint scenario, we select data which contains personal information using a characteristic and select destination outside of the EU using another characteristic. Figure 7.1 Simplified abstract syntax of constraints in our DSL. Besides specifying single characteristic literals, also the selection of multiple literals and the exclusion of literals are possible. Another way of using characteristics is to define characteristic classes which encapsulate the characteristic selection. By using classes, selection can be predefined by an architect and referenced in multiple constraints. This indirection is considered useful in more advanced scenarios. Last, destination selectors can refer to elements of the architectural model created with data-centric Palladio. Using this identity selection, restrictions can be defined more precise and tailored to specific operations or components. Some constraints do not rely on fixed characteristics or sets of characteristics, but rather compare the value of data and destination characteristics. An example are role-based approaches where processes emit data with dynamically set roles. To formulate such constraints, we add characteristic variables and set variables. These variables are defined using data selectors and destination selectors. We add conditions which restrict possible values with regard to other variables. The simplest case is a variable comparison of characteristic variables of data flowing to a destination with other characteristic variables. More complex scenarios which compare characteristic sets using set operations or the conjunction of multiple conditions are also supported. The language elements statement, data selector, and destination selector are obligatory. The condition of a rule is optional and only required if a data selector or destination selector defines a characteristic variable. Regarding the concrete syntax, we aim to provide a modular design which can be easily read by an architect without prior knowledge. Because most of the language elements shown above are non-optional, every rule has the same structure. Data selector, statement, destination selector, condition. This structure is motivated by the constraints formulated in a natural language. Data with certain characteristics never flow to destination with certain characteristics where. Listing 7.1 shows a possible constraint for the geolocation constraints example, which prohibits personal data to flow outside of the EU using RDSL. We describe each compartment in the following sections. Listing 7.1 simplified geolocations constraints example given in concrete syntax. Types and imports. The development process with RDSL is integrated into data-centric Palladio. We reference characteristics and architectural model elements. Prior to using these to define data flow constraints, they have to be properly included from the environment explicitly. We identify the following external information to be relevant. Characteristic types. Data-centric Palladio defines containers which encapsulate the type's name and possible values called literals. They are represented as enumeration. For example, for a characteristic called privacy level, which models the privacy of personal data, possible literals are personal and anonymous. Palladio models. In order to refer to specific nodes or destination of data flows, we need information about the architectural model and its deployment. The latter is stored in the allocation model, which refers to the execution environment model, the system model, and transitively the component repository model. The users model describes the user's behaviors and provides insights on entry points of control and data flow. Combined, these models represent model information of the architecture for which we define data flow constraints. For more information on the Palladio component model, see section 2.2. In the following, we describe how this information is included and processed in order to be used to define data flow constraints. Figure 7.2 shows the abstract syntax of the root container model and contained language elements such as constraints discussed before. The include element is used to import the information specified above from other models. These models are serialized and stored in XML files. Thus, the include statement references these. If constraints only rely on characteristics and don't relate to specific architectural elements, only including characteristic types is sufficient. Otherwise, all relevant Palladio models have to be also included as stated above. Figure 7.2 Abstract syntax of top-level elements. Every model requires a definition of one target model type. We use this explicit definition to separate the constraint formulation from the architectural description, which is represented by the target model type. Possible types are data-centric Palladio and the underlying operation model. We support both model types since the choice only has minor impact on the DSL complexity while giving the architect more flexibility. Besides the target type, architects state which imported characteristic types and Palladio elements shall be used to resolve references. Characteristics have to be explicitly declared before they can be used inside constraints. Using the characteristic type language element, the architect binds types to included characteristic types. This indirection of type definition has multiple advantages. First, characteristic types can be renamed for the usage inside of constraints, which can enhance the understandability of the formulated restriction. Second, not all included characteristic types are sometimes needed, for example, if only a subset of these are required in the defined constraints. Third, this indirection is considered to be more generic regarding the desired target model type. Using separate characteristic type definitions, multiple target models can be supported without the need of rewriting constraints. Other language elements which are directly contained in the root model are constraints and characteristic classes. As outlined in section 7.1, characteristic classes encapsulate one or more characteristic selections. They can be referenced throughout all constraints in the same file and are thus defined independently. We discussed their syntax in section 7.3. Constraints are also directly contained in the model. They are the main language element to formulate data flow restrictions and are explained in section 7.5. Vorjahresreferenzen. Last, we show our exemplary concrete syntax in listing 7.2. Use the import keyword to include external information like characteristic types and Palladio models in line 3 to 5. Defining import statements in the head of a code file is a common practice in many programming languages. We start each file with the definition of the target model type as shown in line 1. We use the keyword target followed by the model type, data-centric Palladio or operation model. Additionally, included characteristic types and Palladio models, which shall be used to resolve references prior to the analysis, are added to a comma-separated list. We reference there by their name without file name extension. The list starts after the using keyword. At least one source with characteristic type definitions is required. We use the type keyword to indicate declaration of characteristics types. A type declaration contains the desired type name for the usage inside constraints and characteristic classes, followed by the name of the included characteristic. An example is shown in line 7. Listing 7.2, concrete syntax of type and import statements. 7.3, selection. With our DSL, we formulate restrictions to data flows in software systems. These restrictions are always applicable to only a subset of all possible data flows. Disallowing all data flows would not yield viable results because any function call would be interpreted as constraint violation. Thus, the selection of data and data flow destinations is crucial. Using data-centric Palladio, the proposed way of selection is by characteristics. Figure 7.3, abstract syntax of data and destination selection as well as classes. In figure 7.3, we show the abstract syntax of data and destination selections called selectors. The majority of these selectors work with characteristics and thus with the characteristic type element discussed in section 7.2. The characteristic type selector is used to select literals from a reference characteristic type. In the following, we enumerate all possible selections using the characteristic type selector. For each selection, we give an example with the characteristic type privacy level, which models the privacy of personal data. Possible literals are personal and anonymous. Single literals. The most basic case of characteristic selection is to select one single literal, R2 and R4. This is the case if, for example, only one type of data is considered in a constraint, for example, only personal data. Multiple literals. This characteristic selection is used if more than one literal are under consideration, R7. There is no maximum number of selected literals. Thus, this selection is only limited by the number of defined literals in a characteristic type, for example, personal and anonymous. Inversion. One or multiple literals can be selected by selecting any literals except one, R6. This is considered to be an inversion, for example, selecting every literals which is not anonymous, which results in the selection of the personal literal in our example. Variables. Variables are used to evaluate multiple selections, for example, by comparing them. R10. Variables do not restrict the selection to a defined subset of possible literals but work as a placeholder. They require the architect to make further assumptions on the conditions part of a rule. We discuss this in this case in the section 7.4. Langsam wird das Bonbon fertig. Aber keine Halsschmerzen mehr. This selection is embedded in the characteristic selector. We use the selection of characteristic literals in two parts of an constraints rule. Falsches N. Das muss da nicht hin. We select data using the data selector, and we select the data flow destination using the destination selector. In figure 7.3, we use multiple inheritance to indicate the combined meaning of selectors being part of a rule and their specific selection goal. Attribute selectors represent both characteristic selectors and data selectors, which are used to define which data is restricted using characteristics. Accordingly, property selectors represent characteristic selectors and destination selectors, determining the restricted data flow destinations using characteristics. We use the terminology of the operational model, which differentiates between properties, characteristics of operations, and attributes, characteristics of data. For more information, see section 6.2. Besides selecting characteristic literal directly inside a rule, characteristic classes can be defined, R8. These classes are not part of a rule and thus can be referenced in any constraint. The use of characteristic class offers multiple benefits. First, it's possible to share characteristic selections among multiple constraints. This does not only speed up development by reusing selections, but also reduces the change impact to a single source rather than changing all affected constraints. Second, multiple selections can be encapsulated into a named class. This enables the architect to name a specific combination of selections and thus enhance the understandability. Characteristic classes contain one or multiple characteristic type selectors. Thus, the selection of characteristics is independent from the later use in data selectors or destination selectors. We define concrete selectors following the same pattern discussed above. Attributes class selectors reference characteristic classes and are used as data selectors. Accordingly, property selector class selectors reference characteristic classes and are used as destination selectors. Last, we discuss node identity selectors. These represent the only selectors which do not depend on characteristics. Instead, they reference architectural elements like components directly, R5. There are two possibilities to identify destinations. If the constraint is defined for the target model type operation model, see section 7.2, the name of the operation is sufficient. Otherwise, the target model type is set to a data-centric Palladio destination is identified using elements from Palladio elements models, which have to be included in advance. For a fully qualified reference, the architect needs to specify the assembly context from an included system model or repository model, a component from this context, and a contained service effect specification. We present our exemplary concrete syntax of selectors and characteristic classes in listing 7.3. Please note that line 5 to 14 do not represent complete constraints, but are intended to show multiple usage scenarios of selectors. For this example, we use the already introduced characteristic privacy with its literals personal and anonymous. Additionally, we use the characteristic location with its literals EU, USA, and Asia. Both characteristics have been introduced in section 4.1. Listing 7.3, concrete syntax of selectors and characteristic classes. Line 1 to 3 shows the definition of a characteristic class. Using this class, all literals except personal are selected in line 2. In our example, that's only true for the literal anonymous. The concrete syntax of such characteristic type selectors starts with the characteristic name privacy, followed by the literal selection not personal. The class name non-personal data reflects this selection. Line 5 and 6 show a characteristic selection used as data selector. Therefore, they are introduced by the keyword data. The keyword attribute indicates the characteristic selector type. Line 5 selects only data with the characteristic privacy set to personal. Line 6 indicates the opposite. Line 7 shows the data selection using an attribute class selector and referencing the characteristic class defined in line 1 to 3. This is indicated by the class keyword. Because the reference characteristic class selects all literal which are not personal, using the class as data selector is equivalent to the selection in line 6. Line 9 to 11 show property selectors, which are both characteristic selector and destination selectors. This is indicated by the keyword node and property respectively. All three property selectors reference the characteristic location. The first statement in line 9 selects all destinations with the characteristic location set to EU. The second statement in line 10 selects all destinations with the characteristic location set to not EU. The third statement in line 11 selects all destinations with characteristic locations set to either USA or Asia. In order to simplify the syntax, the inversion of literals and the selection of multiple literals cannot be combined. The conjunction of multiple inverted selections can be achieved by utilizing multiple data selectors. In our example, the three possible literals are USA, Asia, and the EU. The selections from line 10, not EU, and line 11, all locations literals except EU, are equivalent. Please note that this does not indicate a semantic equivalence. If another characteristic was added afterwards, the selection of both lines would become different again. Line 13 and 14 show node identity selectors as indicated by the keyword identity. If the target model type is set to operation model, destinations are selected by their name using an arbitrary string. In order to identify the destinations using data-centric Palladio, the architect specifies the assembly context, for example, exemplary assembly context, the component, for example, exemplary component, and the service effect specification, for example, exemplary sef. 7.4 Conditions. For some data flow restrictions such as the role-based access control scenario represented in section 4.2, defining rules with fixed values is not sufficient. In order to extend the architect's capabilities, we introduce characteristic variables and characteristic set variables in section 7.3. These variables represent placeholders for possible literals in the analysis process, R10. The initial usage of variables does not restrict the data flow in any way. Thus, architects need to restrict possible values of multiple characteristics variables by evaluating them are 12. This is achieved using the condition compartment of a rule. Conditions are defined to work with variables and sets. In order to make restrictions on their allowed values, we define operations. These operations reference variables and combine them or evaluate them to Boolean statements. Simple examples are testing if two variables are equal or checking if a variable's value is element of another set variable. It's also possible to create combinations of variables, for example by unifying two sets variables literals. Last, operations can be nested, which enables architects to formulate more complex conditions. Figure 7.4 shows the abstract syntax of conditions. In order to enhance the readability, we omit concrete operations and show these separated in Figure 7.6. As discussed in section 7.3, characteristic type selectors refer to defined characteristic types. Instead of binding a selection to specific literals, architects can postpone the restriction to the condition part of a rule by using a characteristic variable type. They either define a new characteristic variable or a new characteristic set variable. Both are required to have a unique name. Characteristic variables represent placeholders for exactly one characteristic literal. Characteristic set variables represent placeholders for a set of characteristic literals. Thus, multiple literals, one literal, or none empty set are possible instances. Figure 7.4 Abstract syntax of conditions. In order to reference these variables in operations, we use references which point a characteristic variable type defined in characteristic type selectors. We use characteristic references to reference characteristic variables, and we use characteristic set references to reference characteristic sets. These references are used from concrete operations, for example a comparison operation, which checks two distinct variables for equality using two characteristic references. In Figure 7.4, we omit all containment relations of references because these belong to concrete operations which inherit from either Boolean operation or characteristic set operation. Operations follow the functional paradigm strictly. They accept one or more arguments, represented by references, and return a single value without any side effect. We classify operations depending on their return type. Characteristic set operations return a characteristic set. Thus, characteristic set references can refer to these operations, nesting, as well as to concrete characteristic set variables. Boolean operations return a Boolean value, either true or false. They can be nested in other Boolean operations, for example the conjunction of two values. We don't define a separate characteristic operation because we don't realize any operation which has a characteristic variable return type. A condition is represented by exactly one Boolean operation. Which concrete operation is used and whether or not multiple operations are nested is up to the architect. We show three exemplary operations and their usage of references in Figure 7.5. The three concrete operations are highlighted gray. The create set operation is used to convert a single characteristic variable to a characteristic set with a single entry, the variable's value. Thus, the operation refers to one characteristic reference. The create set operation is a characteristic set operation and can thus be referenced from other operations which accept a characteristic set reference. An example for such an operation is the empty set operation, which tests a referenced characteristic set for emptiness. Because a set can either be empty or not, this represents a Boolean operation. The logical AND operation accepts two arbitrary Boolean operations and returns a conjunction of these Boolean values. Thus, it represents a Boolean operation itself. We don't use references for Boolean operations because they only exist in the condition and can be nested directly. This is not the case for characteristic variables and characteristic sets, which originate from data selectors and destination selectors and thus have to be referenced. The containment relations in Figure 7.5 show how multiple operations can be nested. For example, a create set operation can be used as argument in an empty set operation using a characteristic set reference. Another example is the conjunction of multiple empty set operations using the logical AND operation. Also, logical AND operations, da fehlt ein Komma, can be nested in other logical AND operations. This approach gives the architect the freedom to formulate complex conditions while only accepting syntactically correct nesting. We discussed this well-formedness of nested conditions operations using the lambda calculus in section 8.1. In total, we define a base set of 11 operations which are shown in figure 7.6. These operations originate from basic literature on set theory. The intersection, union and subtraction of sets are considered to be basic operations to create new sets. We add an operation to convert an element to a set which contains only this element, since elements and sets are not equivalent. Other operations check if a set contains the specified element and if a set is empty. We add operations to test the equality and inequality of variables. In order to create more complex conditions, conditions, knapp daneben, we add three Boolean operations: conjunction, disjunction, or negation. These represent a complete operator system. The selected operations are sufficient to express all constraints from the case study presented in section 6.1. Figure 7.6, abstract syntax of condition operations simplified. We list our selection of characteristic set operations in table 7.1 and our selection of Boolean operations in table 7.2. For each operation, we show the expected arguments, discuss the operation's results, and give a short example. In order to simplify the notation, we use numbers instead of characteristic literals. However, this has no impact on the semantics of these operations. Please note that the examples do not represent our concrete syntax, but rather use mathematical and logical symbols and notations. In order to simplify the base set of operations of our DSL, we exclude several operations which can be expressed by combining included operations. We discuss 4 examples in the following. Here, uppercase letters like A represent set variables, lowercase letters like X represent variables. Table 7.1, all characteristic set operations which can be used in conditions. Test for disjoint sets. A common use is to test whether or not two sets contain no matching items. We exclude this operation since it can be easily expressed by testing if the intersection of two sets contains 0 elements and thus represents the empty set. Formally, distinct A or B is equivalent to A intersected with B equals the empty set. Equality of sets. The equality of sets can be expressed by testing whether or not both sets become empty if subtracted from another. Adding an element to a set. We do not include an operation which adds an element to a set. Instead, we use the create set operation together with the union operation. Fancy. Removing an element from a set. We do not include an operation which removes an element from a set. We use the create set operation together with the subtract operation. Please note that this enumeration is not comprehensive. This is also the case for our 11 selected operations. In order to cope with this problem, we minimize the change impact of adding new operations to the DSL. Figure 7.5 shows that all concrete operations inherit from either Boolean operation or characteristic set operation. Other than that, they only have containment relations to references or operations which are used as arguments. Thus, we can add or remove operations easily without changing the meta model at another point. Last, we discuss our exemplary concrete syntax of operations in the condition part of a rule. Listing 7.4 shows multiple operations which use references and on one characteristic variable variable in line 1 and 2 characteristic set variables in line 2 and 3. Please note that the conditions starting in line 5 do not represent complete constraints, but are used to show multiple usage scenarios of operations. Table 7.2. All Boolean operations which can be used in conditions. Listing 7.4. Concrete syntax of conditions using operations. In order to represent a valid condition, the most outer operation of line 5 to 8 has to be a Boolean operation. This is the case because empty set operations, element of operations, and logical AND operation inherit from Boolean operation. The condition in line 5 evaluates to true if the set represented by the characteristic set variable b has 0 literals. Line 6 evaluates to true if the intersection of the characteristic set variables b and c is empty. The condition in line 7 returns true if the characteristic literal represented by the variable a is also contained in characteristic set b, and line 8 is true if the set variable b has 0 elements but the set variable c had at least 1 and is thus not empty. Using this simple notation, architects can formulate even complex conditions in a straightforward manner. Wow. 7.5. Constraints. We motivated the structure of constraints in section 7.1. In this section, we discuss further details on of constraints and show their concrete syntax using the building blocks presented in section 7.2 to section 7.4. Figure 7.7. Abstract syntax of constraints and their contained elements. We show the abstract syntax of constraints in figure 7.7. A constraint has a unique name and exactly one rule. We model the rule explicitly to enhance the expandability of our DSL, for example by adding the possibility to combine multiple rules. Each rule has exactly one statement which holds details on the control flow restriction, concrete flow restriction. The restriction is defined by its statement modality and its statement type. We also model these explicitly to enable further refinement in future versions of the DSL. Currently, the only possible statement type restricts the flowing property of data. The only possible statement modality is never. Following the foundations of modal logic, other modalities like always are imaginable. Combined, the statement of rules in the current DSL restricts data to never flow. We select data which is restricted to never flow using data selectors and destinations of such flows using destination selectors. Every rule is required to have at least one data selector and at least one destination selector. It's also possible to select data using multiple data selectors, R13, in a single rule. This is not equivalent to selecting multiple literals from a single characteristic, but rather enables the architect to apply further filtering on the selected data by combining more than one characteristic selection. The same is possible for destination selectors. A simple example is considering data security. If, for example, personal data is only allowed to flow outside of an internal server if it's encrypted, this can be achieved by combining a data selector on the privacy characteristic of the data with a data selector on the characteristic which represents the data encryption status. And the data's encryption status. More information on selectors can be found in section 7.3. In some cases, selecting data or destinations by specifying concrete characteristic literals is not sufficient. We define characteristic variables which represent placeholders for possible characteristic literals in section 7.3. If architects use variables, they are required to make further assumptions in the condition part of a rule. Thus, it depends on the data and destination selection whether a condition is required. We discussed the structure and restriction capabilities of conditions in section 7.4. We combine the parts of the concrete syntax of data selectors, destination selectors, statements, and conditions to formulate complete rules and constraints. Listing 7.5 shows the concrete syntax of multiple exemplary constraints. We use the characteristic location with the literals EU, USA, and Asia. Listing 7.5, full-fledged constraint given in concrete syntax. Every constraint starts with the constraint keyword followed by the name of the constraint. The constraint's rule is surrounded by brackets. Both rules contain the required elements. Both rules contain the required elements: data selector, statement, and destination selector. The second constraint additionally uses a condition in line 8. We aim to enable the architect to read constraints like natural language. Thus, we use speaking names as keywords and structure rules following the data flow from source to destination. We use uppercase letters for some of the keywords like never, flows, and where to show a simple partitioning at first glimpse. This approach is influenced by the common declarative database language, SQL. The first, or SQL, je nachdem, wo du auf der Welt bist. The first constraint in line 1 to 3 restricts data which has a characteristic location set to EU to never flow to a destination with this characteristic set, to USA. The second condition in line 5 to 9 is formulated less precisely and therefore uses a condition. Data with a variable location is never allowed to flow to a destination with the characteristic location set to another literal. Thus, the second constraint implies the first one because the literals of location characteristic differ in the data selection and destination selection. However, the opposite is not the case. The second constraint, for example, also restricts data with its location set to Asia to never flow to a destination with the location set to EU. Oh, trivial. 7.6 Example instances. In this section, we present the application of our DSL in real-world examples. We use the language elements represented in the previous sections to describe the constraints from the example scenarios presented in Chapter 4. For each scenario, we summarize its use case and all defined characteristics with their belonging literals. We analyze the constraints and show how they can be formalized using our meta model. This includes a discussion of the usage of our exemplary concrete syntax. 7.6.1 Geolocation constraints. The geolocation constraint scenario in section 4.1 is motivated by legal restrictions, for example from the European General Data Protection Regulations, GDPR. They restrict the flow of personal data and disallow data to be passed to non-whitelisted countries. This constraint does, for example, affect the architecture of an international online shop, which have to synchronize data across borders. However, this is not allowed for personal data. The example instance of geolocation constraints scenario uses a shop server deployed in the EU, while the database server is located in Asia. Using data-centric Palladio, the following characteristics have been defined to model this scenario. The privacy characteristics represent the privacy level of data and is personal if it can be associated with a person. The location characteristic represents the location of deployment of servers and components. The constraint is formulated as follows. No personal information is processed outside of the EU. Following the legal restriction of the GDPR, this can also be formulated in a broader sense. In unsafe locations, it is never permitted to process or store personal data. The second constraint uses an additional classification for safe locations, for example the EU, and unsafe locations, for example Asia, and is thus more extendable. We model both constraints in the following. Figure 7.8 Geolocation constraints example instance using the DSL. Figure 7.8 shows the structure of the first constraint, which prohibits the flow of personal data to destinations outside of the EU. We include an external file types XMI, which contains the characteristics of the architectural model created with data-centric Palladio. We use these characteristics to create characteristics types called privacy and location. These are referred in characteristic type selectors. The attribute selector selects data with the characteristic privacy set to personal. The property selector selects destinations with the characteristic location not set to EU. This is represented by the inverted flag set to true. Both selectors are used in a rule with the statement never flows. The rule is contained in a constraint with the name no flow outside the EU. The alternative constraint from Kunz expands this constraint by classifying locations to be either safe or unsafe. We model this scenario using characteristic classes. Figure 7.9 shows the structure of this constraint. We use a characteristic class called unsafe locations to embed the characteristics type selector used to select all destinations which have a characteristic location not set to the EU. We then reference this class in the destination selection part of the rule using a property class selector. The major benefit of using characteristic classes in this scenario is the interchangeability. Architects can add or remove characteristics and literals in the class without having to change any constraints which reference the class. An exemplary use of this scenario would be to check data flows to various locations. Additionally, they can reference the class in multiple constraints since it is an independent element. Figure 7.9 Geolocation constraint example instance with characteristic classes. Listing 7.6 Concrete syntax of the geolocation constraints example instance. We show the formulation of both constraints using our exemplary concrete syntax in listing 7.6. We define the target model type and include the characteristics definition file in line 1 and 2. We define the characteristics types which are used in the constraints in line 3 and 4. The first constraint, which doesn't use characteristic classes, is shown in line 11 to 13. The second constraint in line 15 to 17. Uses a reference to the characteristic class defined in line 5 to 7. In this example, the selection of both destination selectors is identical despite the fact that the first constraint directly defines the literal, while the second constraint references a class. It's up to the architect whether or not the definition of characteristic class whether or not the definition of a characteristic class is worth the additional effort. (7.6.2) Access control. The second example scenario is based on access control systems like the Unix file system. Prior to accessing any data, the actor's role is checked against the list of authorized roles and of the requested data. We illustrated this scenario in section 4.2 using a simplified version of the travel planner case study. In this example, users request flight offers from a travel agency. They choose an offer and book it by directly contacting the offering airline. This booking process includes the transfer of credit card details, which has to be permitted by the users explicitly. Otherwise, this would represent a privacy violation. Using data-centric Palladio, the following characteristics have been defined to model this example. Both characteristics enumerate the same set of literals. Possible literals are the user, which books the flight, the travel agency, which collects flight offers, and the airline. We use the characteristic roles to model an actor's role and the characteristics access right to model all actors' roles which are authorized to access a specific datum, for example, the user's credit card details. A generic constraint for access control systems like the presented one can be formulated as follows. Data access is only permitted if the actor's role is authorized. An actor is authorized if one of its roles is contained in the access rights characteristic set of the accessed data. Figure 7.10 shows the structure of this constraint. The usage of target model type include and statement is equivalent to the geolocation constraints example explained in subsection 761. We import characteristics types and refer to them using characteristic types. In this scenario, further restrictions to the data flows are defined which cannot be expressed using concrete literals in attribute selectors or property selectors. Thus, we declare two characteristic set variables which are called rights and roles. These variables are defined as part of the characteristic type selector whose attribute isVariableSelector is set to true. This indicates that variables are used which have to be restricted in a condition of the rule. As discussed before, actors, and thus destinations, are only authorized to access data if at least one of their roles is also contained in a data's access rights set. This can be evaluated by the intersection of both sets. If the intersection is not empty, at least one role exists in both sets, which implicates a permitted data access. If the intersection is empty, a violation is found. We model this by using an empty set operation together with an intersection operation. The latter uses two characteristic set references to reference the characteristic set variables created from the attribute selector and the property selector. The empty set operation uses a characteristic set reference to refer to the result of the intersection operation. Figuratively speaking, this represents nesting both operations. Das ist doch trivial. Figuratively speaking, this represents nesting both operations. The empty set operation is contained by the condition which expects a Boolean results. Expects a Boolean results. Eins von beidem. Which expects a Boolean result in the case if the intersection is empty. In this case, if the intersection is empty or not. Figure 7.10, travel planner access control example instance using the DSL. Listing 7.7, concrete syntax of the access control example instance. Listing 7.7 shows the formulation of this constraint using our exemplary concrete syntax. Line 1 and 2 are identical to the geolocation constraints example shown in 7.6.1. We define the target model and import the characteristics from data-centric Palladio. In line 3 and 4, we define the characteristic types needed for the constraint. The constraint is called access rights violation and contains the required element statement data selector in the form of an attribute selector and destination selector in the form of a property selector. Both selectors do not refer to concrete characteristic literals, but define characteristic set variables called rights and roles. The condition refers to these variables by first applying an intersection operation on both sets. The intersection is then checked on its emptiness using an empty set operation. Characteristic set references are used in the syntax but not visible in the concrete syntax. Their main purpose is to connect an operation to its arguments. These arguments can be concrete variables, as seen, for example, in the intersection operation of this example. Alternatively, the arguments are results of other nested operations. While this difference is important for the abstract representation, it is not for the user. Thus, we decide to use a simple concrete syntax motivated by the functional paradigm which omits the internals. To conclude, we want to point out a similarity of the constraint formulated in our DSL with the constraint written in natural language. We consider architects to be capable of understanding the constraint even with no or only little training in data flow modeling. Chapter 8. Language Semantics. In this chapter, we discuss the semantics of our domain-specific language, DSL. The semantics of our language are defined by the mapping from language elements presented in Chapter 7 to parts of executable Prolog programs. This mapping bridges the gap between the architectural domain and the underlying formalism used for the analysis. Additionally, we discussed the mapping of results from the analysis back into the architectural domain. By providing a detailed description of the mapping between both domains, we strive to answer RQ2. We start by giving an overview of the mapping in section 8.1. This includes a discussion of additional dependencies other than the constraints formulated within our DSL. In section 8.2 to section 8.4, we present details on the semantics of individual language elements. We discuss the mapping of analysis results back into the architectural domain in section 8.5. Last, we show two example transformations based on the example scenarios from chapter 4 in section 8.6. Jetzt wird's cool. 8.1 Overview. Our DSL is used to define data flow constraints. In order to analyze whether or not modeled architectures violates these constraints, they have to be mapped to the underlying formalism Prolog. This mapping is realized using a model-to-model transformation from our meta-model presented in Chapter 7 to a Prolog meta-model developed by Cypherman. Generated Prolog models can be serialized afterwards. As discussed in Chapter 5, this transformation is embedded in the process of data-centric Palladio. Thus, we use the existing analysis capabilities at the operation model together with the constraint query API summarized in section 6.2. Prior to the definition of our DSL, architects had to manually define constraints by by writing Prolog code. By using our DSL together with data-centric Palladio, both the modeled architecture and its defined constraints are transformed into Prolog code automatically. The Prolog engine performs the analysis in the underlying formalism by solving defined constraints. The results, a list of 0 or more data flow constraint violations, are transformed back into the architectural domain. The benefit of this additional mapping is the simplified interpretation without the need of knowing the underlying formalism. The result mapping only transforms the results and not the constraints of the architectural model. Thus, our approach is not considered to be round-trip engineering. In order to generate executable Prolog code which interacts with data-centric Palladio environment, we must consider additional aspects as input to our transformation. Strembeck et al. Consider the platform of the DSL execution as software building blocks that provide functions to implement the DSL semantics. Kluge Aussage. Examples are programming languages and frameworks, for example Prolog or the operation model. In our scenario, additional dependencies occur since the transformation of the DSL also relies on the architectural model and its transformation to the platform. Absolute Lieblingsgrafik. Figure 8.1, data flow diagram of the transformation and solving process. Figure 8.1 shows the data flows and thus dependencies between the architectural model and the constraint definitions, their transformation, and the underlying formalism. We use the notation of data flow diagrams presented in Figure 2.1. We model the architectural model characteristics and the constraint query API as data sources because they are lying outside of the context of our system and are considered to be available throughout the whole transformation process. Global constants present another data source which holds naming conventions for different language elements. These conventions can be chosen freely but need to be the same in a DSL mapping and result mapping process. We model the result as datasync, which receives the constraint violations mapped back into the architectural domain. We show the definition of constraints using our DSL as process, which receives information about the architectural model and its characteristics and returns a DSL model as described in Chapter 7. This is the only step in the transformation process which requires user input, for example an architect defining the constraints. The Prolog solving process takes both the mapped results from the model mapping as well as the DSL mapping and uses the constraint query API to analyze the constraints and return Prolog results. There are 3 major mappings in Figure 8.1 which are highlighted gray. The model mapping takes information about the architectural model and the characteristics and transforms these into the operation model. This process is defined by data-centric Palladio. Additionally, a transformation trace is generated which holds transformation instance-specific mapping information. With this information, elements in the transformation output can be traced back to their origin in the architectural model. The DSL mapping is the first transformation we describe in this chapter. We use this mapping to create a Prolog representation of the constraints which have to be analyzed afterwards. The execution of this transformation depends on multiple artifacts. DSL model. This is the major input of the mapping. This model is an instance of the meta model described in Chapter 7 and holds all information about the constraints formulated by an architect. Constraint query API. The transformation generates Prolog code which calls the constraint query API to analyze the transformed architecture model. Thus, the resulting code depends on the definition of the API. Transformation trace. An architect can select data flow destinations by their identity. See section 7.3. The transformation trace is used to resolve the transformed element identities, for example elements of the architectural model. Global constants. In order to simplify this result mapping, we use constants which exist throughout the solving process and in the prologue results. The constants are needed to identify specific variables in the prologue results, for example, by using defined variable prefixes. Wäre mal inkonsistent, hier sind keine Punkte, hier sind Punkte. Hier ist falsch eingerückt. The result of the DSL mapping is the transformed DSL, which is serialized as prologue code and used for the prologue solving process. The results of the analysis represent 0 or more constraints violations, which are mapped back into the architectural domain to be interpreted by an architect. As with the DSL mapping, the execution of this transformation depends on multiple artifacts. Prologue results. The results of the prologue solving process represent constraints violations in the form of bound variables, for example, the specific elements where a violation occurs. These violations are the major input of this mapping. Transformation trace. The results of the analysis are based on the operation model. In order to map them back into the architectural domain, the originating elements have to be resolved. This step is the counterpart to the usage of the transformation trace in a DSL mapping. Global constants. These constants have been introduced by the DSL mapping. They can be used to identify relations in the prologue results which are not represented by the underlying formalism, for example, the meaning of a variable. DSL model. We used information on the originating constraint definition to enhance the representation of mapped results. By combining information about a constraint and its violation, we aim to simplify the interpretation by an architect. In the following, we present simplified results of the transformation in order to show the different artifacts on which the DSL mapping and result mapping depend. We use the geolocation constraints example scenario with the characteristics privacy, personal or anonymous, and location EU, Asia or USA, presented in section 4.1. For the complete transformation, please refer to section 8.6. Listing 8.1 shows the concrete constraint of this scenario. Data which is considered to be personal is not allowed to flow to any location which is not considered to be in the EU. Both selections use characteristics. Listing 8.1, simplified concrete syntax of the DSL prior to its transformation. Listing 8.2 shows serialized prologue which represents the result of the DSL mapping. Please note that this is only an excerpt. The complete generated code can be found in section A3. The clause, which starts at line 1, exists to check if the transformed operation model contains call arguments which violate the constraint discussed above. Call arguments represent the flow of data to a process as argument of an operation. The predicate in line 6 represents the selection of personal data using the constraint query API. Line 7 represents the selection of operations with the characteristic location not set to EU. Listing 8.2, excerpt of the DSL transformation result represented as prologue code. This snippet shows 3 of the 4 influences modeled in figure 8.1. First, the DSL model contains the information on the constraint and influences the usage of selections and characteristics. Second, the constraint query API is used to query the transformed operation model and thus influences the structure of the clause and the used predicates. Third, variable names as query type or OP and prefixes as constraint originate from the global constants. The transformation trace is not used in this example because no operations are selected by their identity. The generated prologue code from the operation model is combined with the generated code from the DSL. Using the latter predicates, goals can be formulated for the prologue solving process. If a prohibited data flow exists, the goal succeeds and a solution with bound variables is returned, which represent a constraint violation. The violation is mapped back into the architectural domain using result mapping. Listing 8.3 shows the textual representation of an exemplary violation. In line 1 to 4, the constraint details are summarized. This information depends on the DSL model input of the result mapping. Lines 6 to 8 show a detected constraint violation. The variables in line 7 and 8 originate from the product results and are assigned using the common knowledge of the global constants. Line 8 shows the call stack, which contains all operations and operation calls which lead to the data flow violation. If the target model is set to data-centric Palladio, the transformation trace is used to map operations from the operation model back to their counterpart in the modeled architecture. Listing 8.3, simplified textual representation of a violation after the result mapping. 8.2, selection. The selection of data and data flow destinations is a key aspect of our language. Every rule defined in our DSL is required to have at least one data selector and one destination selector, see section 7.3. Most selectors refer directly or indirectly, using characteristic classes, to characteristics. In order to explain the mapping of those selectors, we first discuss the representation of characteristics in the operation model and the querying of these using the constraint query API. As described in section 6.2, characteristics are represented as value set types, which are named finite sets of values. In the operation model, data attributes and operation properties refer to these value set types. The assignment of concrete characteristic literals depends on the architectural model. In order to query the operation model for data and destinations with certain characteristics, the constraint query API defines 5 relevant predicates. Data is represented as call argument or return value of an operation or as globally accessible call state. We use the predicate call argument, return value, pre-call state and post-call state to test for flowing data with specific attributes. Destinations are represented as operations. We use the predicate operation property to test for operations with specific properties. In order to combine the selection of data and destinations, we use call stacks, which are used by the operations model to represent every possible control flow through the system. The stack valid predicate ensures that a call stack is correct, which is the case if it represents a possible control flow through the system starting at the usage of an user. By utilizing Prolog's backtracking mechanism, we can test all possible control flows and thus all occurring combinations of data and destinations in the operation model. Figure 8.2, object diagram of 4 different characteristic type selectors. Figure 8.3, abstract syntax tree of a mapped characteristic selector. In our DSL, characteristic type selectors represent the selection of characteristic literals and are referenced by attribute selectors and property selectors. They can select single literals, multiple literals, use inverted selections, or define variables. Figure 8.2 shows these 4 possible combinations which are referenced from a property selector. The leftmost characteristic type selector only selects destinations with the property location set to USA. The next selects only destinations with their locations not set to the EU. The third selects destinations with locations set to either EU or Asia. The rightmost does not define any literals but use a characteristic variable named place instead. We use the operation property predicate to specify the relationship between an operation from the operation model and the characteristics literal. The predicate is used with 3 arguments: the operation, the characteristic, and its literal. If the specified operation has set a specific literal, the predicate succeeds. Figure 8.3 shows the abstract syntax tree of the generated Prolog code. We use the terminology from the Prolog meta model. The generated compound term contains its name, the value operation property, and the 3 arguments: OP represents a variable and is thus represented by another compound term with 0 arguments. Location and USA are fixed values represented by atomic quoted strings. Listing 8.4 shows the prolog code of the transformed selector shown in figure 8.3 in line 1. Line 3 to 8 show the other 3 transformed selectors from figure 8.2. We omit the remaining 3 abstract syntax trees for the sake of brevity. Listing 8.4, prolog code and the transformed 4 characteristic selector types. The second transformed selector in line 3 specifies operations which do not have the characteristic locations set to EU. This is realized using prolog predicate, which evaluates to true if its argument cannot be proven. The third selector accepts multiple literals from the same characteristic. This is realized in line 5 and 6 using prologs or predicate, which evaluates to true if one of its 2 arguments evaluates to true. The last mapped selector in line 8 does not specify literal but declares a new variable. Declare war. Further details on this variable behove to the mapped condition part. In order to identify the variable as characteristic variable, it is prefixed with the global constant var. Attribute selectors are mapped in a similar way using the predicates discussed above. Call argument, return value, pre-call state and post-call state. Since we analyze a data flow as a whole and not its direction, the transformed results uses them all. Additionally, a call stack variable is generated and tested for validity using the stack valid predicate. Prolog code, listing 8.5, prolog code of a transformed attribute selector and a property selector. Listing 8.5 shows the combination of a mapped attribute selector together with a mapped property selector and a generated call stack variable. The call stack variable is unified in line 1. Using prolog list syntax, we bind a variable OP to the head of the list S. The underscore indicates that the remainder of the list is unspecified. The stack valid predicate in line 2 ensures that the list S represents a correct call stack. The operation property predicate in line 3 tests the operation at the top of the call stack OP for its characteristic location. This represents the leftmost selector shown in figure 8.2. Line 4 uses the call argument predicate to test if a parameter P holds the literal personal of the characteristic privacy. If the predicate therefore uses the operation at the head of the list S, we ensure that the parameter P belongs to the operation OP using the predicate operation parameter in line 5. All these predicates are combined using prolog's built-in conjunction predicate. In addition to the call argument predicate, other data-related predicates, return value, pre-call state and post-call state have to be used because we do not consider the data flow's direction, only its existence. However, this does not alter the structure of the code snippet presented in listing 8.5. We show other predicates in listing 8.6, which can be used instead of the call argument and operation parameter predicate in line 4 and 5 of listing 8.5. The arguments of these predicates are similar. In order to cover all data flows, these have to be combined using multiple clauses. Listing 8.6, return value and call state predicates. Another selector type are node identity selectors. These selectors don't select destinations by their characteristic, but rather by their identity, which is represented by the destination's name. This can be represented in prolog by unifying the operation variable OP with the atomic quoted string which holds the name, for example OP equals destination name. However, this simple mapping is only possible if the defined DSL constraint targets the operation model. If the target model type see section 7.2, reference data-centric Palladio, the following additional steps are required to correctly resolve the targeted operation. If a constraint is defined for a data-centric Palladio, destinations are referenced by a component is assembly context and a service effect specification. All these elements are contained in the architectural model for which the data flow constraint is defined. In order to reference the correctly named operation in the operation model, the transformation of the originating architectural model has to be traced. This is achieved using the transformation trace, which is an additional output of the model mapping. See figure 8.1. The transformation trace holds all mappings from a concrete architectural model to the operation model. It can be queried using an interface of data-centric Palladio and returns the name of the mapped operation in the operation model. This name is then used for the prologue unification. This additional resolution step is also needed for the names of characteristics and their literals using by attribute selector and property selectors. Figure 8.1 shows the characteristics are another input of the model mapping. If constraints are defined for data-centric Palladio, the mapping of characteristics and literals has to be queried using the transformation trace. Besides referencing characteristics directly to select data and destinations, characteristic classes can be used. They also select attributes inside an attribute class selector and property inside a property class selector, but define the selection independent from the referencing constraint. Thus, they represent an indirection. For more information on characteristic classes, see section 7.3. Listing 8.7 shows a simple example of a characteristic class which selects location which are literals as EU or USA using the location characteristic in line 1 to 3. Das Line habe ich mir überlegt, das steht ja nicht da. Additionally, a property class selector in line 5 refers to this class. Listing 8.7, concrete syntax of characteristic class and attribute class selector. We show the generated prologue code from the transformation in listing 8.8. Please note that this snippet doesn't represent a completely transformed constraint, but is only used to illustrate the mapping of characteristic class. These classes are mapped to separate clauses like characteristic class EU or USA in line 3. For each selection of a class, two terms are generated. First, the value set member term in line 4. This belongs to the constraint query API and is used to ensure that the variable represents a literal from the specified characteristics, for example, location. Second, we add a predicate in line 5, which is used to select the specified literals. Line 1 and 2 are facts, which represent this selection. Using Prologue's backtracking mechanism, we ensure that one of them exists and is member of the characteristic locations in order to make the second clause succeed. Listing 8.8, prologue code of a transformed characteristic class and its referencing. Characteristic classes are defined independently in our DSL and are also transformed independently to their use in constraints. They are defined for characteristics in general and neither bound to attributes or properties. This binding is defined later in line 7. This line represents a destination selector as described above. The major difference is that instead of specifying a concrete literal, for example EU, a variable is inserted. This variable is then used together with the predicate from the transformed characteristic class in line 8. If the prologue engine is requested to prove the term of the operation property in line 7 for a specified operation OP, the following steps happen. The unbound variable with the name class_var EU or USA location is detected and tried to resolve using the term in line 8, which refers to the clause from the transformed characteristic class in line 3. Using the value set member predicate, the range of possible values is reduced to all literals of the location characteristic, for example, EU, USA, and Asia. Then, Line 5 further reduces possible values to EU and USA. By utilizing backtracking, both values are tried to bind to the variable in order to prove the operation property term. This succeeds if the specified operation is labeled with one of these characteristics as stated in the original DSL selector. The example shown in listing 8.8 uses several prefixes and postfixes defined in the global constants. We use these to identify the usage of variables and to avoid naming conflicts. Without this decoration, a characteristic called, for example, OP, might collide with the identical named term which represents an operation. Additionally, we use an iterator for all transformed selectors of a characteristic class because there is no restriction how many selectors can be contained by a class for a single characteristic. This is similar to rules which can contain any number of data selectors but at least one. Jetzt ist noch eine Nummer abgefahrener. 8.3 Conditions. Besides specifying concrete characteristic literals, data selectors and destination selectors can define characteristic variables which represent single literals or set of literals. If such a variable is defined, an additional condition is required which defines further restriction on a variable's value. In order to define these restrictions, a number of operations can be used. Examples are testing if a variable's literal is contained in another characteristic set or if a characteristic set is empty. For more information, see section 7.4. In order to define a mapping from conditions to Prolog, 3 domain gaps have to be bridged. The mapping of characteristic variables, the transformation of single operations to Prolog predicates, and the representation of the structure of nested operations of an abstract syntax. The mapping of variables, which are introduced in characteristic selectors, is similar to the mapping of characteristic classes. Instead of using a constraint query API like operation property with a constant literal, a new variable is introduced. We've shown this above in listing 8.4. We use simple variables to represent characteristic variables and lists to represent characteristic sets. This is motivated by the strong support for lists by the Prolog language. For our usage scenario, lists without duplicate entries are close enough to the semantics of sets. Prolog's documentation also refers to sets as unordered lists without duplicates. Listing 8.9 Selector defining a characteristic set variable and the mapped result. To obtain all possible literals of an attribute or property, we use Prolog's built-in findAll predicate. Listing 8.9 shows a destination selector with a characteristic set variable in line 1 and a transformed result in line 3. The findAll predicate accepts a template variable, a goal to solve, and a list to store all results. The predicate tries to satisfy the goal, in the case of the operation property predicate, using backtracking. All successful unifications with the template variable iterator template are stored in the list var set R. The prefix var set originates from the global constants and is used to mark the variable as characteristic set variable. Table 8.1 Mapping of operations of a condition to Prolog predicates. Huiuiui. Haben wir ganz schön was gedacht. A condition consists of operations which have to be mapped. Fortunately, Prolog's lists library already contains several common predicates, for example intersection or union. These predicates are defined for sets, lists without duplicates, and thus suppress duplicates. An example is the union predicate which filters duplicates while two lists are combined. Table 8.1 shows all operations which can be used inside conditions and the predicates they are mapped to, if hidden S. We provide a short example for each predicate. Although the mapping of operations to Prolog's built-in predicates is straightforward, the mapping of the structure of nested operations needs additional effort. The condition in our DSL follows the functional paradigm strictly. Operations accept only one or multiple arguments and return exactly one return value. There exists no states or side effects. Additional variables other than characteristic variables defined in selectors cannot be declared. On the other hand, Prolog follows the logic paradigm. Using facts and rules, goals can be proven. This is realized by binding all variables in a term. A goal succeeds if all variables can be bound without conflict. The term x equals 3, x equals 4, unify with 3 and unify with 4, will always fail because there is no possible value for x which satisfies both terms. The term x equals 3 or x equals 4, unify x with 3 or unify x with 4, always succeeds. Prolog doesn't have concepts like return values from functional programming. Goals can either be proven and all variables bound, or the goal is not provable. KAPITEL and others also encountered this gap while mapping the object constraint language OCL to Prolog. In order to map nested operations from the functional paradigm to Prolog, we have to make up for the missing concept of return values. To do so, we introduce new Prolog variables for every transformed operation. The only exceptions are logical and, logical or, and logical not, which can be transformed directly. We discuss a simple example for the usage of these variables in the following. Listing 8.10 shows two, ich habe das da oben noch nicht vorgelesen, Figure 8.4, abstract syntax of an exemplary condition in the DSL. So. Listing 8.10 shows two nested operations in line 1 and the transformation Prolog code in line 3. The condition term tests if the intersection of two characteristic sets is empty. This is mapped to a length predicate and intersection predicate as described above in table 8.1. The characteristic set x and y are mapped to Prolog variables using the var set prefix from the global constants to mark them as set variables. In order to combine the statements of both predicates in line 3, a new variable temp0 is introduced. The Prolog engine unifies the set variables and binds the result to the new variable. Using this variable, the length predicate is tried to satisfy, which only succeeds if the variable represents an empty list. Listing 8.10, nested operations and their Prolog counterpart. We illustrate this gap using abstract syntax trees. Figure 8.4 shows the tree of the condition formulated in our DSL. The nesting is realized using a characteristic set reference in the empty set operation. This reference can either refer to a nested operations or the concrete characteristic variables. Thus, an architect can nest an arbitrary number of operations. Figure 8.5, abstract syntax tree of the transformation to Prolog of an exemplary condition. Figure 8.5 shows the tree of the transformation results in Prolog. The compound term which represents the intersection and length predicate are not nested in each other but rather combined using an AND predicate. This also shows why logical operations, namely logical AND, OR and logical NOT, don't need additional variables. They can be directly mapped to the Prolog counterpart. In the following, we summarize the process of transforming nested operation to Prolog terms. Algorithm 1 shows the pseudocode of our algorithm. We present the mapping of three different operations. Logical AND operation, which represents Boolean operations with Boolean arguments. Empty set operation, which represents Boolean operations with a set as arguments. And intersection operation, which represents operation with sets as arguments and as return types. All other mappings are defined similar to these examples despite the fact that they have different number of arguments. The algorithm accepts a Boolean operation as input, which is contained by the condition element, see section 7.4. The output is a stack of Prolog compound terms which can be combined using AND predicates. The mapping is started by calling the map function in line 4. In the shown excerpt, 3 functions with different argument types exists. The logical AND operation, mapping in line 5 to 11, transforms a conjunction into the DSL using the conjunction to a conjunction in Prolog. Therefore, left and right subtrees of the conjunction are mapped independently. The call of a map function always results in a transformed Prolog term lying on top of the stack E. After both subtrees are mapped and stored in variables, the conjunction of both is pushed back to the stack E to be used in the surrounding operation or returned as result. The empty set operation is shown in line 12 to 16. This operation accepts a reference to a characteristic set variable or a reference to a nested operation which returns such a variable. This is realized using the resolve operation, which accepts a reference. If this is a reference to a real variable used in a selector, the variable is pushed back on the variable stack V in line 28. Otherwise, a variable is pushed to the stack in line 32 and the operation mapped next with which binds the variable. This represents the nesting of operations. Calling the resolve function at the start of the mapping, like in line 13, 18 or 19, ensures that either the variable itself lies on the variable stack V or an additional variable lies on the stack V together with the operation which binds this variable lying on the stack E. Das lassen wir mal eine Sekunde lang stehen zum Studieren. Algorithm 1, mapping algorithm of conditions from the DSL to Prolog. Afterwards, this variable is popped from the stack in line 14 and used to create the compound term with the length predicate in line 15. This term is then pushed to stack E. The mapping of the intersection operation in line 17 to 24 works similarly. Instead of one characteristic set reference, the operation expects 2 references which explains both resolve calls in line 18 and 19. However, an intersection operation does not return a Boolean value but a characteristic set which has to be further evaluated. Thus, the variable which is bound to the results of the intersection is not popped but left on the stack in line 22. The variable has to be used by the surrounding operation which nested the intersection operation. It is ensured that such an operation exists because only Boolean operations are allowed as entry point of a condition. We illustrate the usage of this algorithm by discussing the single transformation steps of the condition shown in listing 8.10 and figure 8.4. The algorithm starts with the empty set operation as input and calls the accurate map function in line 12. This mapping calls the resolve function in line 13, which recognizes the reference to an intersection operation and thus maps this nested operation first using the accurate map function in line 17. Prior to executing this mapping, an additional variable is generated and pushed on the variable stack V in line 32. The mapping of the intersection operation starts by resolving the variables by calling resolve twice in line 18 and 19. Because these references real characteristic set variables, no further nesting is required and both variables are pushed to the stack onto the existing variable. Afterwards, both variables are popped from the variable stack V and used to create the first compound term with the intersection predicate in line 23. Additionally, the variable, which is now again head of the stack, is referenced but not popped from it. Last, the created compound term is pushed to the stack E in line 23 and the function returns the control flow to calling resolve function, which returns to the mapping and the surrounding empty set operation in line 13. In line 14, the variable was left on the variable stack v is popped from it and used afterwards to create a compound term with the length predicate in line 15. This term is pushed to the stack E in line 16. Then the control flow returns to line 4 and the algorithm ends with two compound terms in the stack E which are combined afterwards using prologues and predicate. The result is shown as abstract syntax tree in figure 8.5 and serialized in line 3 of listing 8.10. Das erklärt alles das. Geil. 8.4 Constraints. After constraints have been defined using our DSL, they are mapped to Prolog code. Afterwards, the generated code is combined with the transformed architectural model as input for the product solving process. In previous sections, we discussed the mapping of single parts of a constraint, for example, the selection of data and destinations in 8.2, section 8.2, and the definition of conditions in section 8.3. In order to be analyzed, these individual elements have to be combined after the transformation. The result is a prolog clause which can be queried in the analysis process and combines all mapped predicates. In section 8.2, we discussed that multiple predicates of the constraint query API can be used to query data attributes: call argument, return value, pre-call state, and post-call state. To create a comprehensive result of constraint violations, all predicates have to be evaluated separately. Thus, we map each characteristic selector 4 times in separate rules. To identify which query predicate returned a constraint violation, we add an additional query type variable to each rule. This variable is unified with a string representing its type, for example, query type equals call argument. This variable is combined with the result of the selector mapping using prologues and predicate. If characteristic variables are used to select data or destinations, the mapped condition is also added. The 4 clauses are then combined using prologues or predicate in one clause which represents the complete constraint. To associate violations to their originating constraints, another unification of a variable with the constraint name is added. The final predicate can then be satisfied by the prolog engine. Listing 8.11 shows the general structure of the complete prolog code generated from a single constraint, called exemplary constraint in this example. Defined characteristic classes are transformed independently and also added to the result as shown in line 1. Moreover, listing 8.11 shows several prefixes and postfixes which originate from the global constants. They are used to prevent any naming conflict of the transformed rules. Listing 8.11 Complete structure of transformed constraints. The statement never flows, which is used by all constraints, is implicitly mapped. The semantics of this statement is to blacklist certain data flows. The analysis selects the blacklisted data flows and returns violation of these restrictions. Thus, no further negation or inversion of complete constraints is necessary. This discussion is supported by the fundamentals of temporal logic. Statements use the modality never. The negation of never, always, not, can be formulated as at least once or eventually. More formally, lange lebe temporale Logik, pure Liebe. Thus, finding violations which represent evidence to the contrary of the modality never is the proposed analysis approach. This relationship between formulated constraints and analysis results has also been identified by Kunz. In order to interpret the results of the product solving process, all relevant variables have to be declared as arguments in the head of the generated rules. Although prolog goals only succeed if all variables can be bound without conflicts, the variables' values are not shown to the user if they are not declared as arguments in the queried predicate. Moreover, we do not only use a static set of variable names like query type or OP, but rather create custom variables for characteristic variables and characteristic classes. To obtain all relevant violation details, we gather variables used in the generated rules. This enhances the prologue results and simplifies the interpretation for the architect after the result mapping. Often, variable names are used in more than one rule. For instance, all rules shown in line 10 to 16 in listing 8.11 use the variable OP, which represents the operation under consideration. When these rules are used together in line 5 to 8, it's sufficient to include the variable's names as arguments in the surrounding rule once. Table 8.2, possible arguments created by the mapping of constraints. This collection approach is embedded in the mapping of constraints to prologue clauses. When a predicate is used inside a clause's body, all arguments are collected and used as arguments of the surrounding clause as well. This ensures that the predicate, which represents the entry point to the prologue solving process, contains all necessary arguments. In listing 8.11, the clause's argument in line 3 are represented by the union of the arguments of all used predicates in line 5 to 8 together with the variable constraint name. We show possible arguments in table 8.2. We also state if the argument's appearance depends on other properties of the mapped constraint. For instance, variables which represent the selection of a characteristic class are only generated if a selector references such a class. For each constraint violation, the argument's values are returned after the prologue solving process. Result mapping. The prologue code which results from the DSL mapping is combined with the code generated from the transformation of the architectural model. The prologue solving process yields 0 or more constraint violations. In order to ease the interpretation, these violations are mapped back into the architectural domain by the result mapping. In section 8.1, we summarize the influences of this mapping. Besides the raw prologue results, information on the transformation trace, global constants, and the constraint originating from the DSL model is necessary. In the following, we discuss these influences and how they are used to abstract from the underlying formalism. The prologue solving is used to prove a goal which is represented by the main predicate, which is created by mapping a constraint. The prologue environment tries to prove this goal, which succeeds if at least one constraint violation is found. Otherwise, the environment yields false, which is mapped to the simple statement, no constraint violation was found. If the goal succeeds, the predicate's argument's bound values are returned. A simple prologue result, which is represented by bound variables, is shown in listing 8.12. We consider this to be the main input of the result mapping. Listing 8.12, raw prologue result of a single constraint violation. This result shows the values of all arguments discussed in section 8.4. This state leads to a constraint violation. The prologue output contains information about a constraint in line 1 and 2 and about a data flow in line 3 to 6. The values in line 3 to 6 represent elements from the operation model. This model is only used by the underlying formalism. Using the transformation trace, we can resolve the originating elements from the architectural domain. In this example, line 3 to 5 represent elements from the modeled architecture, and the value in line 6 represents a characteristic literal. The names of the variables in line 1 to 5 and the variable's prefix in line 6 originate from the global constants. By using the same constant's name in the DSL mapping and the result mapping, we simplify the identification of the variable's meaning. These constants are required to match in both mapping executions. The prefix class_var in line 6 indicates that this constraint references a characteristic class. However, the prologue result does not offer any information about the usage or details of this class. We use the original DSL model as additional input to the result mapping to fill this gap. We identify 4 different tasks in the result mapping. We summarize these in the following. 1. Mapping basic variables. Variables like OP and ST represent the point in the system where the constraint violation occurred. Mapping these variables is considered to be the minimal information which is needed by an architect in order to interpret the results. To interpret the analysis results. The mapping of these variables depends on the global constants as well as the information trace. Mapping the call stack. The call stack represents the stack of operations in the operation model and is used internally to query possible data flows. However, this information can also be useful to trace back the call sequence which leads to the constraint violation. Thus, it's mapped back using the transformation trace. 3. Mapping class variables. For each reference characteristic class, a variable is generated which holds the selected literal which leads to the constraint violation. The variable is identified by its prefix from the global constants. Afterwards, information about the characteristic class is gathered using the variable's name and the DSL model. Combined, this mapping yields the parameter its literal and the reference class. 4. Mapping characteristic variables. For each characteristic variable which is used in a selector, a variable is created. After the prolog solving process, this variable is bound to the literal which leads to the constraint violation. We map each variable's value using the transformation trace. In addition to the mapped prolog results, we also process all constraints from the DSL model and summarize their restrictions. We consider the combination of information about a constraint, for example, which data and destinations are selected, and information about a constraint's violation, for example, literal combinations and a call stack, to be easier to interpret. After the result mapping, we serialize the results and show them to the architect. In order to minimize the change impact of different concrete representations of map results, we decoupled the mapping and the serialization process. Currently, we support the creation of plain text files as well as the markdown format. Using the latter, information like variable assignment and call stacks can be represented as tables. Additionally, the presentation of variable values benefit from more formatting options. We implemented the conversion of the abstract result mapping result to the concrete representation using the template pattern. Thus, other representations can be integrated easily. A conceivable possibility would be the graphical representation integrated into diagrams of the architectural model. Listing 8.13 shows an exemplary serialized result mapping. First, general information about the scenario, the constraint, and the violation is shown in line 1 to 7. In line 9 to 12, we show constraint details. In this example, data is selected using 2 characteristics and the destination is selected using a characteristic class. Last, all constraint violations are enumerated. For each violation, a short summary is displayed. Afterwards, additional information like the call stack or selected literals from the characteristic class are shown. Any information which is not used by the constraint under observation is omitted. For instance, no characteristic variables or conditions are used by the constraint in this example. The result mapping and the serialization adapts to the formulated constraint. Listing 8.13. Complete textual representation of mapped constraint violations. Example transformations. In this section, we show the application of the mapping in real-world examples. We used scenarios presented in Chapter 4, which were already used to discuss the language syntax in section 7.6. We discuss the constraints and their transformation results and compare them to constraints formulated using the underlying formalism. Additionally, we show exemplary constraint violations and the mapping of these results back to the architectural domain. 8.6.1 Geolocation constraints. The geolocation constraints scenario deals with the flow of personal data motivated by legal restrictions. The example scenario models an online shop which operates inside the EU but uses servers which are deployed in Asia. The constraint prohibits personal data to flow outside the European Union. Therefore, 2 characteristics have been defined. The privacy characteristic states whether data is personal or anonymous. The location characteristic represents the deployed location. In this scenario, possible locations are EU, USA, and Asia. Listing 8.14 represents the constraint using our exemplary concrete syntax. In addition to the basic constraint shown in line 5 to 7, a more generic approach is shown in line 9 to 11. Instead of prohibiting personal data to flow outside of the EU, unsafe locations are defined using a characteristic class. This class is shown in line 1 to 3. Although both constraints represent different analysis goals, they yield the same constraint violations in this scenario. Listing 8.14 shortened concrete syntax of the geolocation constraint example scenario. We transform both constraints to the underlying formalism using our DSL mapping. We use the operation model as target model in order to simplify the generated Prolog code. Listing 8.15 shows an excerpt from the transformation result of the first constraint. For the sake of brevity, we only show the main predicate in line 1 to 4 and the clauses generated to handle call arguments in the line 5 to 11 and return values in line 14 to 20. We leave out the generated code which handles call states. The full generated Prolog code can be found in section A3. The clause in line 1 to 4 unifies the constraint name variable to the original name of the constraint. This information is needed in the result mapping step to associate single results with their originating constraints. Afterwards, all predicates for handling data flows are referenced. In this example, only call arguments and return values are under considerations. Both clauses contain a unification of the query type variable followed by the use of the call stack. Afterwards, data is selected using the call argument predicate in line 11 and the return value predicate in line 19, together with the selection of the data flow destination using the operation property predicate. In listing 8.16, we show an excerpt from the transformation result of the second constraint. Here, we only consider the handling of call arguments. Line 1 to 4 show the transformation result of the characteristic class, which is referenced by the second constraint. The location EU is denoted as fact in line 1, which is then used in line 4 inside the predicate which represents the class. The predicate is referenced in line 17 together with the selection of the destination using the operation property predicate in line 16. Listing 8.15 excerpt of the DSL transformation result of the first geolocation constraint. Listing 8.16 excerpt of the DSL transformation result of the second geolocation constraint. The additional variable class var location, which holds the selected literal, is used as argument in both predicates in line 6 and 10. This enables the result mapping to display the variable's concrete value to the architect in case of constraint violation. We compare the semantics of the transformed constraint to the original constraint from Kunz. In natural language, he describes the Prolog constraints as follows. Does an operation O exist within any call sequence where for any parameter P of O the privacy is personal and the deployment specified by the location property of O specifies an unsafe location? This definition is equivalent to the predicate shown in line 10 to 17. Using Prolog's backtracking mechanism together with the stack valid predicate in line 13, any possible call sequence is queried. The selection of any parameter with the matching characteristics is performed by the call argument predicate in line 15, and the location is selected using the operation property predicate together with the unsafe locations characteristic class in line 16 and 17. As discussed before, both constraints yield the same violations because they select the same data and destinations. In the following, we discuss the Prolog results and its mapping back to the architectural domain. Listing 8.70 shows an exemplary constraint violation represented by the raw Prolog solving output of the second constraint using characteristic classes. This result holds the unification for data flow related variables like OP and S, but also mapping related information like the constraint and type of query where the violation was found. Listing 8.17 Prolog solving result of the geolocation constraint scenario. Listing 8.18 shows the mapped result. First, information about the constraint is presented in line 1 to 12. Then all constraint violations are listed. Therefore, the result from the analysis is processed. In this example, the violation occurs because of a store operation on a database which is deployed in Asia and which handles personal customer data. Listing 8.18 mapped result of the geolocation constraints scenario. 8.6.2 Access control. The second scenario is based on role-based access control. In this case study, the flow of sensitive data from a travel planner smartphone application to a travel agency and an airline is modeled. We use characteristics which represent the roles of these actors and access rights to different types of data. For instance, the access to credit cards details is only permitted to roles authorized by the user. This can be formulated by comparing an actor's roles and the access rights for each datum. If the intersection is empty, no authorized role can be found and thus a constraint violation occurs. We repeat the constraint using our exemplary concrete syntax in listing 8.19. We use characteristic set variables which represent roles and access rights in line 2 and 3. In line 4, we reference these variables to create condition, condition which tests the emptiness of the intersection of both sets. Listing 8.19 shortened concrete syntax of the access control example scenario. Constraint. In listing 8.20, we show an excerpt from the transformation result using our DSL mapping. The predicates contain two additional arguments, varset rights and varset roles. These represent the characteristic set variables from the model constraint. In line 10 and 11, Prolog's findAll predicate is used to collect all possible roles for the system state under consideration. The intersection of these roles is then tested for emptiness using Prolog's list and set operations in line 12. Listing 8.20, excerpt of the DSL transformation result of the access control constraint. We compare the semantics of the transformed constraints with the constraints formulated by Kunz. He describes a Prolog constraints which finds access control violations as follows. Does an operation O exists within any call sequence where for any parameter P of O with the attribute authorized roles, no role R exists so that both P authorized roles are and O roles are true. The iteration over operations is possible. Call sequence is achieved using the call stack from the operation model in line 7 and 8. We collect authorized roles of the parameter under consideration with the first findAll predicate in line 10. The access roles are collected with the second findAll predicate in line 11. Being true causes the appearance of a role in one of the two sets. Thus, the lack of existence of at least one role in both sets can be formulated as test for emptiness on the intersection of both sets as described in line 12. We show an exemplary Prolog result after the Prolog solving in listing 8.21. In addition to the unification of generated variables like the constraint name and the call stack, the assignment of both characteristic set variables is shown in line 6 and 7. In the results shown here, an actor with the role airline tries to access data which is only allowed to be accessed from actors with the role user. The intersection of both sets represents the empty set and thus a constraint violation. This can be expressed as follows. Roles intersect rights equals empty set. Listing 8.22 shows the map result. After the general information in line 1 to 7, we show the constraint details in line 8 to 13. Both the data and destination selection display the use of characteristic set variables. The condition is printed as defined in the DSL. We choose to display the function in its original shape because we consider description of the condition in natural language to become confusing quickly. Listing 8.21, exemplary Prolog solving result of the access control scenario. Und dann Listing 8.22, mapped exemplary result of, also darum geht es eigentlich gerade. Afterwards, the constraint violations are displayed in line 15 to 18. For each violation, the values of all characteristic variables are displayed in addition to the basic information like the call stack or which operation call caused the violation. This information is especially helpful after the problem location has been identified in order to understand the property of the data causing it. The serialization to plain text files prints all variables and their values as list for each constraint violation. Alternatively, we implemented a serialization which creates markdown files. Here, variables and their values are displayed as simple table, which is considered to enhance the readability, especially for constraints, which utilize many different characteristics variables. Und jetzt fängt der Spaß erst an. Chapter 9. Evaluation. In this chapter, we present the evaluation of our approach. We evaluate the domain-specific language, DSL, as well as the mapping between the architectural domain and the underlying formalism. In order to minimize the risk of collecting unrelated meaningless data, we use a goal-question metric plan. Basili et al. Proposed defining goals first and then deriving questions of interest. While goals are on a conceptual level, questions are on an operation level and try to characterize the object of measurement. Metrics are then used to collect quantitative data to evaluate questions and measure the fulfillment of previously defined goals. There is already work on DSL quality and the development of DSLs available. This work identifies several quality attributes of DSLs such as simplicity, uniqueness, consistency, space economy, and the choice of the right abstraction level. We present goals and resulting questions in section 9.1. In section 9.2, we explain the evaluation design which is used to answer these questions. We present and discuss the evaluation results in section 9.3. Afterwards, we discuss threat stability in section 9.4 and limitation of our approach in section 9.5. We close with information on the availability of the data to reproduce our evaluation in section 9.6. Goals 9.1 Goals and questions. The goal of this evaluation is to show whether or not the research questions presented in section 1.1 have been answered satisfactorily. In research question RQ1, we ask about architectural level constructs fehlt ein which oder sowas. Oder being oder, also. We ask about architecture level constructs are necessary to define data flow constraints. Okay. Research question RQ2 asks for a mapping of these constraints from the architectural domain and the underlying formalism, as well as a mapping of analysis results. Based on these research questions, we derive evaluation goals. We evaluate the expressiveness of the DSL, RQ1, and the usability and space efficiency as proposed by other work presented above. In order to evaluate the mapping between the architectural domain and the formalism RQ2, we evaluate the equivalence of the analysis. We define the following evaluation goals. G1. Expressiveness. The domain-specific language shall provide concepts which allow the versatile constraint specification for different applications. G2. Usability. The domain-specific language shall improve an architect's analysis productivity by reducing the task complexity. G3. Space efficiency. The domain-specific language shall be concise without verbose elements or structures for small and larger problem specifications. G4. Equivalence of analysis. The transformation of the domain-specific language to the native formalism shall preserve the semantics. Goal G1 evaluates the expressiveness of our DSL. A high expressiveness indicates that many architectural level constructs are supported and thus many data flow constraints can be expressed using our DSL. In order to discuss the expressiveness, we analyze the formulation of different constraints derived from related work, Q1. Additionally, we discuss the usage of well-known terminology and the analysis environment provided by data-centric Palladio. This includes an evaluation whether the supported concepts to formulate constraints on variable sets and sets are sufficient, Q2. To evaluate G1, we define the following questions. Are the supported DSL concepts sufficient to formulate constraints in the context of data flow modeling? Q2. Does the DSL constraints offer required concepts to reason about characteristic variables and characteristic sets? Page and others stress the importance of simplicity and usability of a DSL. The expressiveness of a DSL has to be paired with decent usability in order to add value to the architect's analysis process. Thus, we evaluate the usability with goal G2. First, we discuss the abstraction from the formalism which is used for the analysis, Q3. Next, we discuss the DSL conciseness and generalization, Q4. A too large degree of conciseness makes the practical usage of the DSL more difficult, with a too high degree of generalization might lead to more abstract concepts which are hard to understand. Additionally, we evaluate typical language properties like orthogonality, Q5, and uniqueness, Q6. Orthogonality increases the understandability of constraints because language features do not overlap and thus can be considered one at a time. The concept of uniqueness ensures that multiple language elements cannot be used to express the same constraint, which leads to confusion while learning the language as well as while reading code written by other architects. Ultimately, we consider We consider the knowledge required to use our DSL in comparison to the underlying formalism, Q7. To evaluate G2, we define the following questions. Q3. Does the DSL provide abstraction from the underlying formalism to the architectural domain? Q4. Is the DSL concise without a too high degree of generalization? Q5. Does the DSL provide orthogonality, avoiding overlapping features? Q6. Does the DSL follow the rules of uniqueness, avoiding multiple ways to express the same constraints or analysis goals? Q7. How much and which knowledge is required to use the DSL for defining data flow constraints? Goal G3 evaluates the space efficiency of our DSL. First, we consider lower and upper bounds regarding complexity. The DSL shall be applicable for simple analysis without requiring much boilerplate code. Q8. This would cause simple analysis goals to be hard to define and hard to read, which also harms the usability. On the other hand, the DSL shall be applicable for larger constraints and analysis goals with multiple goals as well, Q9. Last, we compare the space efficiency of the DSL with the underlying formalism, Q10. Here, we consider not only the absolute difference in effort to write equivalent constraints, but also the scalability of the DSL compared to the underlying formalism with growing number of reference elements and defined constraints. To evaluate G3, we define the following questions. Q8. Can the DSL be applied to formulate simple analysis without requiring much boilerplate code? Q9. Can the DSL be applied to formulate large analysis without being verbose? Q10. Does the DSL improve space efficiency compared to the underlying formalism? Last, we evaluate the equivalence of the analysis results in goal G4. Without doubt, expressiveness, usability, and space efficiency are important properties of a DSL. However, a language created to define constraints becomes less useful if the mapping to the formalism used for the analysis is error-prone. An erroneous transformation might lead to different analysis results in comparison to constraints defined directly using the underlying formalism. Due to the importance of this topic, we choose to analyze the preservation of semantics by performing a correctness proof, Q11, as advised in the domain of compiler construction. Additionally, we compare analysis results from different constraints formulated both using our DSL and the underlying formalism, Q12. To evaluate G4, we define the following questions. Does the transformation preserve semantics, Q11, and Q12, does using the native formalism compared to the transformed DSL yield the same constraint violations and thus analysis results? (9.2) Evaluation design. In this section, we discuss the evaluation design and how we strive to answer the questions presented above. In order to avoid overfitting of a DSL, we use additional scenarios other than the exemplary scenarios introduced in Chapter 4. We briefly present all studied scenarios in section 9.2.1. Afterwards, we discuss the evaluation design for each goal in subsection 9.2.2 to subsection 9.2.5. 9.2.1 Studied scenarios. Prior to the definition of our DSL, we collected requirements from scenarios from related work which define constraints on the flow of data. We described this approach in section 6.1. In total, we identified 7 different scenarios. We choose 2 scenarios as input for the requirement analysis process. First, the geolocation constraint scenario, which uses 2 different constraints to restrict the flow of type 0 and type 1 data. We consider them from now on separately to the major difference in the goal formulation, see section 6.1. Second, we analyze the travel planner case study. In the following, we describe all 8 scenarios which will be used throughout the evaluation whenever applicable. Geolocation type 0 data. This scenario describes an online shop which handles personal data. Personal type 0 data is not allowed to be stored in unsafe locations. For more information, see section 6.1. Geolocation type 1 data. This scenario also describes an online shop which handles personal data. Personal identifiable information is not allowed to be joined with data from other origins. For more information, see section 6.1. Geolocation constraints using encryption. This scenario was defined by Kunz by altering the original geolocation constraints scenario. The context remains the same, describing an online shop which handles personal data. Additionally, a characteristic is defined which describes the encryption status of data. Instead of using a location characteristic to describe the deployment of services, the constraint prohibits the flow of personal but unencrypted data to a specific element of the architecture. Travel planner. This case study originates from the iFlow approach and has been also used to evaluate previous work in the context of data-centric Palladio. It describes the flow of data through a travel planning smartphone application. For more information, see section 6.1. Contact SMS Manager. This scenario also originates from the iFlow approach and describes the interaction of two smartphone apps, a contact manager and an SMS manager. The latter is only permitted to access a subset of personal contact data when authorized by the contact manager. This constraint is another instance of the access control restriction presented in section 4.2. Distance tracker. This case study also originates from the iFlow approach and describes a fitness app which tracks the GPS position of the user. Afterwards, this data is sent to another service for further evaluation. However, this service is not allowed to gather information about the user's current position. This constraint can also be realized based on the access control example. UMLSec secure links. This scenario originates from UMLSec and is used to validate the secrecy of selected data. Therefore, an attacker with a set of capabilities, for example read or delete, is modeled. Additionally, the transmission of the data under consideration is described. The constraint analyzes different combinations of attackers and transmission types. For instance, an attacker might delete an encrypted data transmission but cannot read, nicht ready, the data. Also da war ich müde. Da habe ich 10 Stunden am Tag geschrieben. Die fucking Evaluation, ey. Ist 40 Seiten, by the way. Wir sind noch lange nicht fertig. UMLSec secure dependencies. This scenario also originates from UMLSec and describes a structural security analysis. This analysis verifies whether or not specified security requirements such as secrecy or integrity are fulfilled by all classes which depend on a selected interface. Therefore, the analysis checks whether all connectivity of dependent classes satisfies the requirements. 922 G1 Expressiveness. The first goal of this evaluation is the investigation of the DSL's expressiveness. An expressive DSL enables the user to formulate many different scenarios without being limited by the number of power of language concepts and elements. In Chapter 6, we described two approaches. First, analyzing real-world case studies as lower limit of the desired expressiveness. We named this the top-down approach. Second, the analysis capabilities of the underlying formalism as upper limit of the power of our DSL. We described this approach being bottom-up. Question Q1. First, we discuss whether or not the current state of our DSL satisfies the collected requirements sufficiently and covers all required concepts. We use all scenarios described in subsection 921 to complete our selections for the top-down approach. This enables us to test whether or not the expressiveness is sufficient to formulate constraints for 8 scenarios in total. Please note that this selection is not exhaustive but represents all scenarios gathered in this thesis. Second, in order to provide a bottom-up evaluation, we compare the expressiveness of our DSL with the Constraint Query API by Kunz. This API is used by the underlying formalism to validate constraints against the transformed architecture. We briefly described its capabilities in section 6.2. Our mapping to the underlying formalism uses this API as well as all constraints directly formulated as Prolog code without the use of our DSL. Thus, this represents the upper limit of analysis possibilities of the current version of data-centric Palladio. This API consists of 24 Prolog predicates in total. We evaluate whether each of the predicates can be expressed in our DSL explicitly or implicitly. We consider a predicate to be expressed implicitly if it is either used by the API together with an explicitly expressed predicate, or if it is implicitly created by our mapping but not explicitly formulated by an architect. Third, we discuss which of our requirements from Chapter 6 have been fulfilled. Requirements which have been gathered from real-world use cases but have not been fulfilled indicate a limited expressiveness of our DSL. Thus, we analyze the coverage of requirements. Question Q2. The highest degree of freedom in goal formulation is offered by the condition part of our DSL, described in section 7.4. Architects can define precise conditions using operations from set theory. we discussed the completeness of the set operations supported by our DSL. In order to answer this question, we performed a literature research on set theory to collect operations on elements and sets. We also include operations from the list library of SVE Prolog, which are applicable on sets. For each collected operation, we show whether it was included or excluded. For all excluded operations, we show whether or not they can be expressed by combining included operations. In order to combine multiple operations on sets and elements besides nesting, we added Boolean operations to the condition part. We discussed the completeness of selected Boolean operations with regard to propositional logic separately. 8.2.3 G2 Usability. The second goal evaluates the language usability. Often, the evaluation of usability-related topics includes the execution of user studies. Due to the effort of executing such studies with a representative selection of subjects, we chose to evaluate usability by objective measures. This evaluation is focused on the abstract syntax, since this represents the major contribution of Chapter 7. However, we include a discussion of our exemplary concrete syntax whenever applicable. Question Q3. One major goal of the DSL is to provide a sound abstraction from the underlying formalism. With our DSL, we abstract from the Prolog programming language and the constraint query API, which is used for the analysis of data-centric Palladio. In order to evaluate the abstraction, we analyze the required effort of different change scenarios in our DSL compared to native Prolog code. Here, less effort indicates good abstraction because the constraint formulation is closer to the real problem under consideration. In order to enable a fair comparison between the DSL and Prolog, we use handwritten Prolog code instead of generated code from our DSL mapping process. Otherwise, we would run into danger to evaluate the DSL mapping instead of the abstract syntax. We only consider change scenarios which originate from the architectural domain because these are closer to changes in real constraint specifications. We collected change scenarios by iterating over all elements of the abstract syntax. We omit two strongly related scenarios, for example, changing variable references in different types of operations, which has similar change impacts independent from the selected operation. Furthermore, we do not consider scenarios where elements are deleted, since these yield the same numerical results as equivalent scenarios where elements are added to constraints. We collected the following 15 change scenarios. Constraint creation. Change a constraint name. Change a characteristic literal of a characteristic type selector. Change a characteristic type of a characteristic type selector. Change a condition variable name in a characteristic type selector. Change a characteristic literals inversion in an attribute selector. Change a characteristic literals inversion in a destination selector. Change a attribute selector to a reference in a characteristic class selector. Change a node identity selector name. Change a characteristic set operation. Change a Boolean operation. Add a characteristic literal to a characteristic type Add a characteristic literal to a characteristic type selector. Add a data selector to a constraint. Add a destination selector to a constraint. Add a characteristic class and a characteristic type selector. Add a condition and a Boolean operation. Oh god. The first scenario, S0, is no real change scenario but included for reference. In this scenario, a minimal constraint with one attribute selector and one property selector is created. The constraint's name is changed in scenario S1. The scenarios S2 to S8 represent basic change scenarios in different data selectors and destination selectors. The scenarios S9 and S10 represent simple change scenarios in a constraint condition. Last, the scenarios S11 to S15 represent the expansion of the basic constraint. They range from minimal additions like a new literal in S11 to larger changes like the addition of a new characteristic class in S14 or a condition in S15. We measure the change effort of these scenarios by counting the requirement atomic steps and distinguish between minor and major changes to formulated constraints. We consider the change of an attribute value or adding or removing arguments as minor change impact, while consider adding or removing domain elements as major change. We count the changes using the abstract syntax for our DSL and the prolog meta model for constraints formulated within this formalism. Additional effort which is required to prepare the constraints in change scenario as 0 is excluded. The measurement always starts with semantically equivalent constraints in both domains. Question Q4. We discussed the DSL's conciseness. A major strength of DSL is the language capabilities to create specifications with less verbosity than the underlying formalism. However, there is an upper limit of the usability of concise language concepts. If the degree of generalization is too high, the language becomes hard to learn and hard to use. In order to measure the DSL's conciseness, we analyze which language concepts are used how often in total throughout all scenarios described in subsection 9.1. Language concepts which are seldomly used indicate a too high degree of generalization and shall be examined more closely. However, this is no comprehensive review because we do not consider our selection of constraints to be exhaustive in the first place. The choice of evaluated concepts is based on the abstract syntax of our DSL. The more often a concept is utilized, the better. We evaluate how often the following language concepts are used. Constraints and rules. Characteristic types and characteristic type selectors. Characteristic classes and characteristic class selectors. Attribute selectors. Property selectors. Node identity selectors. Conditions, Boolean operations. Characteristic set operations. Question Q5. A language benefits from a high degree of orthogonality because this allows the user to interpret language concepts independently. Language orthogonality can also be described as independence of modeling concepts. Orthogonality violations might cause unwanted dependencies between seemingly unrelated elements, which leads to worse maintainability and understandability. We evaluate the orthogonality of constraints formulated in our DSL based on the structure presented in section 7.1. Data selectors, destination selectors, statement, and condition. The discussion is based on relations in abstract syntax which indicate coupling between different parts of the DSL. Question Q6. Languages which satisfy uniqueness avoid providing more than one way to express semantically identical specifications. Page and others state, by avoiding duplication of features, the language is kept smaller and more explainable. However, uniqueness shall not be mixed up with the sacrifice of feature. It only favors smaller subsets of powerful features that might be useful in more than one context. In some cases, uniqueness and expressiveness become mutually exclusive. This requires the careful consideration by the language designer. Our evaluation of uniqueness is twofold. First, we analyze the mapping between concrete syntax and abstract syntax. Here, a uniqueness violation would cause confusion which elements from the concrete syntax is correct or the best one to describe a constraint. Second, we analyze the uniqueness of different concepts of our language, also by taking the semantics of different elements into consideration. Here, the tolerance of uniqueness violation is higher due to the trade-off between expressiveness and uniqueness. Still, every violation must be weighted up carefully. Question Q7. We discuss the knowledge which is required to define constraints using our DSL in comparison to the underlying formalism. We discuss distinguish between complexity which is essential to a problem and complexity which is added by accident because of the choice of abstraction or environment. An abstraction like the use of DSLs benefit from minimizing accidental knowledge. Wohl eher complexity, aber okay. This enables new users to learn the DSL more quickly and understand constraints written by other architects more easily. However, it's hard to quantify knowledge. Therefore, we focus on which knowledge is required and discuss the amount qualitatively. We get at different domain concepts and terminology which influences the process of defining constraints with or without the use of our DSL. This includes knowledge on the syntax and the modeled architecture under consideration, but also the analysis environment. As discussed above, complexity, which is introduced by the environment and requires knowledge, can be essential or accidental. Based on an analysis process described in Chapter 5 and a transformation overview discussed in Section 8.1, we identify the following domains and concepts. K1. Data flow diagrams and architectural modeling. For example, knowing how to define architectures and use the terminology proposed by data flow diagrams. This is essential to the modeling domain. K2. Data-centric Palladio. For example, knowing how to use the modeling environment and define concrete models using Palladio. This is essential to use both approaches. K3. The architectural model in use and its characteristics, for example, knowing about model data and the characteristics names in literal. This is essential to the architect. The DSL mapping and result mapping, for example, knowing details about the transformation and the internal processing. This adds to accidental complexity. Global constants, for example, knowing about the names and usage of these constants, which also adds to accidental complexity. K6. Operation model and constraint query API, for example, knowing about the structure of the model or how to use single API predicates. This is also considered to be accidental complexity when using the DSL. Transformation and trace, for example, knowing about the resolution of transformed elements or how to manually resolve them. Manually resolving traces is considered to be accidental complexity and thus avoidable. Prolog. For example, knowing about a logic paradigm, about basic syntax, and about common predicates. This is essential when using the underlying formalism. The DSL. For example, knowing about the structure of constraints and the concrete syntax. This is essential when using the DSL. Additionally, we discuss which knowledge is required in order to interpret the analysis results after the result mapping. Ideally, no further knowledge is required other than the knowledge needed to define the constraints using our DSL. G3. Space efficiency. The third goal evaluates the language space efficiency. A space-efficient language can reduce the effort required by modelers and tools in order to maintain the models. As already discussed in usability-related questions, there is an upper limit for space efficiency to improve the language. A too high degree of space efficiency harms the usability by impairing the readability. To evaluate space efficiency, we consider constraints of different sizes, which could also be named scalability. However, we choose the term space efficiency to clarify that the scaling factor under consideration is the number of language elements required to describe a certain specification. This includes discussing the concrete syntax of these elements. We do not consider analysis or transformation performance, since both are out of scope and not considered to become critical. Question Q8. We discussed the formulation of simple analysis goals using RDSL. We construct a minimal constraint which uses only mandatory parts of the rule. We analyze the space efficiency regarding the abstract and concrete syntax and discuss the trade-off between maximizing space efficiency while retaining the same readability. Question Q9. This question discusses the opposite of question Q8. We consider large analysis such as big constraints with many elements. We investigate vertical composition by adding more elements to a constraint and horizontal composition by adding more constraints. To evaluate the verbosity of bigger constraints, we construct a constraint which contains all element types of all types of elements of the abstract syntax and discuss its readability. Additionally, we discussed the UML-sec secure link scenario, which is considered to have large penis. Constraint. Question Q10. We compare the DSL's space efficiency with the space efficiency of constraints formulated in the underlying formalism. Thereto, we recreate constraints formulated with the DSL using handwritten Prolog code. We don't use generated Prolog code from the DSL mapping in order to exclude the mapping performance from the consideration and thus provide a fair comparison to the native formalism. This question is related to the discussion of abstraction in question Q3. In question Q10, we don't consider change effort but count the concrete number of elements on different constraints. Therefore, we use the abstract syntax of the DSL and the Prolog meta model. We utilize all expressible constraints from the scenarios described in subsection 921. We also include the minimal constraint from question Q8 and a comprehensive constraint from question Q9. We evaluate the absolute number of model elements as well as the growth of these numbers for bigger constraints. Since all constraints differ in their structure and use different language elements with different intensities, this enables us to evaluate the space efficiency of these elements compared to native Prolog code. In order to gain additional insights, we perform the change scenarios S11 to S15 from question Q3, which adds different elements to the constraints under consideration. 925 G4 Equivalence of Analysis. The fourth goal evaluates the equivalence of the analysis using the DSL compared to the underlying formalism. We define the equivalence as receiving the same analysis results which represent the same constraint violations. Formulating constraints using our DSL shall yield the same results as defining similar constraints using Prolog code and a constraint query API. This goal is important because different analysis results can significantly decrease the benefit gained by using the DSL as abstraction to the underlying formalism. Question Q11. Die hat's in sich. Due to the importance of this topic, we use a formal correctness proof to evaluate the preservation of semantics. A transformation preserves semantics if the semantics of the language elements are equivalent to the semantics of the transformed result. This approach is motivated by Narayanan and others, which checked whether the semantics of the input model were preserved in the output model of a transformation for graph transformations. Figure 9.1 shows the structure of correctness proofs performed, for example, in the domain of compiler construction. This approach is based on Morris' advice as well as discussion by Thatcher and others and Daiber. This figure shows the transformation. Jetzt wird es natürlich haarig, weil, Alter, wie lange ist es her, dass ich das letzte Mal griechische Buchstaben gebraucht habe? Ich habe das vor 2 Jahren geschrieben. Ich ignoriere das mal gekonnt. The figure shows the transformation of a source language into a target language. In our scenario, the source language is represented by the DSL, the target language by Prolog code using the constraint query API, and the transformation by the DSL mapping. Both languages use semantics, which map an arbitrary, well-formed language construct to a meaning. This mapping depends on the language contexts, which are transformed by P. So weit komme ich dann doch noch. In our scenario, this context is defined by data-centric Palladio and its operation model, respectively. Last, the source semantics, which are defined by the source semantics. The source meanings, which are defined by the source semantics, shall imply the target meanings defined by the target semantics. If this encoding is erroneous, the interpretation or execution of code in the target language would not behave as defined in the source language, which would break the correctness. In our scenario, this would yield a different analysis result. Figure 9.1 adapted diagram of Morris on compiler correctness proofs. In order to prepare this proof, we formalize several aspects of our DSL. This includes the source language, the source semantics, and the transformation. Other parts of this proof originate from other work. The constraint query API is part of the target language and its semantics have been defined by Kunz. The source context and target context have been defined by Cypherman and others. In order to construct this proof, we present the formalization of these concepts. Ultimately, we perform a structural induction to show the encoding for varying language combinations but fixed transformation rules. We use universal algebra to formalize the language and transformation as proposed by Jackson and others to reason about semantics of DSLs. Universal algebra enables us to define a set of n-ary function symbols for encoding the modeling concepts, which can be nested, naturally expressing relations over relations. Jackson and others define a domain by enumerating all concepts, components, and primitives in a structure. The set of all possible model realizations is denoted by in the following, we only consider well-formed model realizations. Transformation rules, as defined by our DSL mapping pattern, match against the input model realization and generate an output model realization. Accordingly, a transformation is a free tuple of disjoint signatures of both domains and a set of transformation rules. The signatures are derived by enumerating all domain concepts of the source language and target language, respectively. A transformational interpretation is a mapping between model realizations following the rules. Last, we consider the semantics of our language by defining a mapping based on propositional logic. This interpretation evaluates given domain elements from the source language to true or false. Accordingly, the mapping evaluates domain elements from the target language. We use these mappings to describe the structural induction. Our goal is to show the encoding for every possible realization of the domain which is implied by the source language. We note the implication between the source meanings and target meanings as follows. The source meanings are denoted by applying the mapping on an arbitrary source model realization. This mapping originates from semantics of the source language. The transformational interpretation is used to transform the realization to a target model realization based on the transformation. Using the semantics of the target language, we denote the meanings of this transformed realization. By testing this implication for every source model realization using a structural induction, we prove the encoding of meanings. Warte mal kurz. Also, für alle, die jetzt gerade zuhören, damit ihr auch wirklich mal was lernt. Also, Compiler-Baubeweis, okay, da habe ich den ganzen Kram her und es ist 2 Jahre her. Ich weiß wirklich nicht mehr so viel darüber. Aber die Idee ist eine strukturelle Induktion. Das heißt, eigentlich ist der geile Kram der Teil hier. Der sagt eigentlich nur, dass die Transformation von mir, von meiner DSL in den zugrunde liegenden Formalismus, also nach Prolog, dass die nichts kaputt macht. Also, dass die Semantik, die Meanings, die ja enkodiert sind durch die Semantik, in der DSL-Welt die anderen implizieren. Ja, das ist dieser Pfeil hier. Und dieses für alle ist jetzt einfach nur eine strukturelle Induktion. Denn ich kann ja nicht für alle möglichen DSLs, also das geht ja nicht. Ich kann ja nicht unendlich viele bauen. Ich kann empirisch das machen, das kommt gleich in Frage 12. Aber ich kann das auch beweisen, induktiv, indem ich mit dem kleinstmöglichen anfange und dann immer mehr draufpacke. Eine strukturelle Induktion. Das ist nicht nur graue Theorie, die man im 2. Semester Informatikstudium lernt. Das kann man tatsächlich einsetzen für solche Beweise. Und das ist in natürlicher Sprache kurz beschrieben, das, was ich hier eigentlich gemacht habe. Und das ist für eine Masterarbeit im Bereich der Softwarearchitektur mit einer bereits so ausführlichen Evaluation die Definition von Overkill. War mir aber egal. Okay. Question Q12. We compare the analysis result of transformed constraints from our DSL with constraints formulated in the underlying formalism. Therefore, we gathered specified constraints from other work and reformulated the constraints using our DSL. Since the collected constraint specifications originate from other evaluated theses, we treat them as gold program. We classify each result of our transformed constraints as true positive, accepted a valid violation, true negative, rejected an invalid violation, false positive, accepted an invalid violation, or false negative, rejected a valid violation. This enables us to use the metric of binary classification. Precision equals true positive divided by true positive plus false positive. Recall equals true positive divided by true positive plus false negative. Please note that questions Q11 and Q12 not only use different approaches, but also evaluate different aspects of the language semantics. Question Q11 focuses on the defined semantics of a language, while question Q12 includes the formulation of constraints based on real examples from other work. Thus, the latter also evaluates the applicability of the DSL semantics, while the formal proof only discusses its correctness. In this section we present 9 free results and discussion. Natürlich, also jetzt geht's los. Bis jetzt alles in der Evaluation. Ne? Das war wirklich nur dafür da, um zu beschreiben, was ich eigentlich evaluiert habe. Und das in der strukturierten und nachvollziehbaren und vor allem für andere Wissenschaftler möglich nochmal durchzuführen, reproduzierbaren Art und Weise. Ne? So, und jetzt kommen die Ergebnisse der Evaluation. 9.3 Results and Discussion. In this section, we present and discuss the results of our evaluation. In subsection 931 to subsection 934, we discuss the results for each evaluation goal separately. Afterwards, we summarize the results in subsection 935. 931 G1 Expressiveness. The first goal G1 evaluates the expressiveness of our DSL. Question Q1 discusses whether the DSL is discusses whether the DSL covers all required concepts, while question Q2 focuses on the expressiveness of the condition part of a constraint. Question Q1. This question is threefold. First, we evaluate the expressiveness in a top-down approach by utilizing constraints from other work. Afterwards, we discuss the upper limit of expressiveness by analyzing the mapping to the underlying formalism in a constraint query API in a bottom-up manner. Last, we discuss whether all requirements represented in Chapter 6 have been satisfied. As discussed in subsection 921, we collected a total of 8 scenarios which can be used to answer this question. 3 of these scenarios have already been used as input to the requirement process. In the following, we show whether or not the scenarios can be expressed using our DSL. If a constraint cannot be expressed, we discuss the missing elements. If a constraint can be expressed, we show a short excerpt how it could be formulated using our exemplary concrete syntax. Geolocation constraints type 0 data. This constraint can be expressed by formulating a simple rule with basic characteristic type selectors and characteristic class. Geolocation constraints type 1 data. This constraint is formulated by joining 2 different data flows which cannot be expressed in the current version of our DSL. See subsection 6.1. Geolocation constraints using encryption. This constraint can be expressed by combining multiple data selectors which work with different characteristics with a node identity selector. Travel planner. This scenario was used to gather requirements for the condition parts of constraints. Its constraint can be expressed by using characteristic variables and 2 operations. Contact SMS Manager. Distance Tracker. Beides mal dasselbe. This scenario is another instance of role-based access control systems. It can be expressed by using the same constraints as shown for the travel planner scenario. Distance tracker same. UML-sec secure links. This scenario models an attacker with varying capabilities which tries to attack different protected parts of a system. It can be expressed by using multiple characteristic classes and constraints. UML-sec secure dependencies. This analysis verifies security requirements of dependent elements of a software system. It cannot be expressed due to the lack of support for the L-not predicate of the constraint query API and the DSL mapping. However, it would be possible to support this predicate without changing the abstract syntax of our DSL. The DSL is capable of expressing 6 out of 8 constraints, or 75%. Next, we discuss our bottom-up approach. We collected all 24 predicates of the constraint query API defined by Kunz and evaluated whether these can be expressed using our DSL. Thereto, we review the DSL mapping and discuss the explicit and implicit uses of these predicates. We consider a predicate to be expressed implicitly if it's either used by the API together with an explicitly expressed predicate, or if it's implicitly created by our mapping but not explicitly formulated by an architect. Table 9.1 shows the result of this analysis. Most of the predicates from the constraint query API can be expressed. However, most of them are implicitly generated or used inside the API in order to aid the constraint analysis. 5 predicates cannot be expressed at all. In total, 19 of 24 predicates, or approximately 80% of all predicates, can be expressed. The high number of implicitly expressed predicates can be explained with the additional abstraction of our DSL. Especially the predicates in the type information category can be used for both testing or as generators when writing constraints using the underlying formalism. Because of the fixed structure of constraints in our DSL, which never allow the flow of data, there is no need for an architect to specify these generators by hand. Last, we discuss whether or not the requirements represented in Chapter 6 have been satisfied. We use these requirements to define a goal for the expressiveness of our language. Thus, not satisfying a requirement can be considered to be a lack of expressiveness. In total, we defined 13 language requirements. We realized the structure of constraints R1, the selection of data R2 and destinations R4, using characteristics, the selection of elements by their identity R5, the inversion of selections R6, the selection of multiple characteristic literals R7, and the creation of classes R8. Additionally, we created characteristic variables R10, characteristic set variables R11, conditions R12, and enabled the combination of multiple selectors R13. Table 9.1 Expressiveness of predicates of the constraint query API. However, 2 requirements were not realized. We did not add a data selector which is able to select data by its type, R3, because this can also be modeled using characteristics which have already been discussed by Kunz. An alternative representation would be to add an additional attribute to the data. Second, we did not realize the consideration of multiple data flows in one constraint, R9. Together, these gaps explain why the DSL is not capable of expressing the type 1 constraint from the geolocation constraints example explained above. To sum up, these results indicates an overall good expressiveness. 75% of tested constraints can be expressed utilizing 80% of the predicates offered by the constraint query API. This has been achieved by realizing 11 of 13 language requirements. Please note that this is no exhaustive answer. It cannot be assumed that this collection of scenarios or constraints is comprehensive. By extending the DSL mapping, this number could be improved. However, in order to receive optimal results, the syntax of a DSL has not been altered by adding support for multiple data flows. This is considered to be a major change, but feasible due to the orthogonal structure of constraints. See question Q5 for details. Question 2. The condition part of our DSL offers multiple operations to define precise conditions on characteristic variables. Due to the high degree of freedom in the condition part, we evaluate its expressiveness separately. First, we analyze the selection of operations and elements and sets. Afterwards, we discuss the nesting and combination of these operations using propositional logic. Table 9.2 shows 18 operations which we collected from literature and the list library of SVI Prolog. We denote whether an operation is included or excluded. If an operation is excluded, we state whether it's expressible using other included operations. We included a set of basic operations which enable the architect to express most of the collected operations. With the 8 operations included, we can express 16 of 18 operations, or approximately 90%. We discussed the possibility of expressing excluded operations by combining included operations in section 7.4. However, the set of selected operations is not minimal. For instance, we included operations for both equality and inequality of variables, which can also be expressed using logical negation. The discussion whether or not a language should only include a minimal set of operations is not considered to be expedient. This is also supported by the fact that most modern programming languages support more than the absolute minimum of required operations. We excluded the operation power set because the concept of a set containing other sets is not expressible using our type system, and we found no real constraint which would profit from this feature. This is also the case for the operation element count. We consider testing for emptiness of sets to be sufficient for most constraints. However, adding other operations on existing types, for example testing for disjoint set, is considered to have a low change impact due to the use of polymorphisms. In order to combine multiple operations on sets and elements beside nesting, we added Boolean operations. The combination of and, or, and not represents a functionally complete set of operations, thus allowing architects to express any combination of operations using propositional logic. It should be noted that this set is also not minimal. Collected operations on elements on set, table 9.2. Table 9.3, change effort of different DSL change scenarios. (9.3.2) G2, usability. The second goal, G2, evaluates the usability of our DSL. Question Q3 evaluates the abstraction from the underlying formalism, question Q4 discusses the conciseness, and question Q5 evaluates the language's orthogonality. Question Q6 checks whether the language satisfies uniqueness, and question Q7 asks which knowledge is required to use our approach compared to the underlying formalism. Question Q3. This question asks whether our DSL provides a significant abstraction from the underlying formalism. Therefore, we analyze the change effort for one constraint creation scenario and 15 different change scenarios. We measure atomic change operations. So, das können wir auch mal sehen hier. We measure. Bin ich falsch abgebogen? We measure atomic change operations and categorize them into major changes, for example, adding new elements, and minor changes, for example, changing an existing value. Table 9.3 shows the change effort of these scenarios. First, we compare the effort to create a constraint in our DSL compared to the underlying formalism. Both constraints shall yield the same analysis result. The effort to create a constraint using Prolog and the constraint query API is twice as much as using the DSL. The scenarios S1 to S10 represent simple change scenarios, for example, renaming a constraint or changing the selected literal. Scenarios S1 to S4 and S8 to S10 show no difference in effort at all. Other scenarios require less effort using the DSL. Only the replacement of class references in scenario S7 requires more effort when using the DSL. This is the case because the Prolog representation only requires the replacement of terms, while the DSL requires a new selector. In the scenarios S11 to S15, elements are added to the constraint. The difference between the difference between the DSL and Prolog code is similar to the change scenarios discussed above. However, scenario S15 shows doubled effort using the DSL in comparison to Prolog. This can be explained by the representation of operations and references to characteristic variables in the DSL. Prolog is well suited for clauses which include the processing of elements and lists. In summary, the change effort of the evaluated change scenarios is smaller on average. There are less changes required, which are also smaller. This can be seen when comparing the difference in major and minor changes. This indicates good abstraction of the DSL from the underlying formalism. Prolog is a high-level programming language with much more formulation possibilities than provided by our DSL. Thus, achieving large difference in the required effort is considered to be difficult. Question Q4. We evaluate the DSL's conciseness regarding the degree of generalization. A too low degree of conciseness lowers the language abstraction, while a too high degree of generalization impairs the language readability and usability. We measure how often different concepts of our language are used in the constraints considered in this thesis. Here, low numbers indicate a possibly too high degree of generalization and shall be discussed. Table 9.4 shows the relation between concepts of our DSL and their usage in the scenarios. Concepts C1 and C2 are used in every scenario, which is implied by them being required parts of every constraint. Attribute selectors C4 and property selectors C5 are also commonly used among all scenarios. Condition-related scenarios C7 to C9 are used whenever variable characteristic literals are under consideration. The most infrequently used concepts are characteristic classes C3 and node identity selectors C6. However, we don't consider them to be a threat to the language's conciseness. Characteristic classes are motivated by constraints written in natural language. In more than one case, architects use characteristics as pattern, for example by defining unsafe locations. Node identity selectors are used to identify elements from the architectural model. In theory, this can always be achieved by defining a new characteristic and applying a literal only to one element. However, this workaround violates the semantics of selecting an element, which can be achieved more directly using node identity selectors. As discussed previously, our collection of scenarios is not comprehensive. Thus, these numbers can only be seen as indicators. Das ist die Tabelle, um die es gerade ging. Table 9.4, Usage of Modeling Concepts in Case Study Constraints. Question Q5. This question evaluates the language's orthogonality. High orthogonality is indicated by independent language concepts. This influences other desired properties like readability, maintainability, and scalability. The discussion of orthogonality is based on the abstract syntax. In section 7.1, we presented an overview of the abstract syntax of our DSL. Here, we discussed the different parts of a constraint: its statement, data selector, destination selector, and condition. This structure is also shown by the concrete syntax: data selector, statement, destination selector, condition. The division of constraints in different parts already indicates good orthogonality. However, in order to give a comprehensive review, wo ist Casey, wenn man ihn braucht, we discuss all relations between these parts and the rest of the abstract syntax. An overview of the complete abstract syntax can be found in figure A1. The statement of a rule is defined completely independent to other parts of the constraint and thus preserves orthogonality. Data selectors and destination selectors are defined mostly independent. Both can rely to characteristic type selectors and characteristic classes. These obtain other characteristic type selectors, which ultimately refer to characteristic types. Characteristic type selectors, which are contained directly in data selectors or destination selectors, are independent from each other. They only might share common references to characteristic types. None of these references are cyclic. Additionally, characteristic classes are defined independently from their use inside of characteristic class selectors. In summary, all relations are unidirectional and none of them are considered to be strongly coupled. Thus, all elements can scale independently and the orthogonality is preserved. Another interaction between parts of a constraint are characteristic variables. These variables are defined and contained in characteristic type selectors, which are used by attribute selectors and property selectors. The variables are referenced from inside the condition part to specify the restriction on the variable's values. In order to decouple this relation, we introduce characteristic references. The references are used by operations inside the condition part to either reference variables or other operations. They represent the only way to interact with variables and are defined unidirectional. In summary, all parts of constraints have a different concern, do not overlap, and are only loosely coupled. Thus, we assume a high degree of orthogonality. Question Q6. Languages with a high degree of uniqueness avoid duplication of features which enhance the language's understandability. First, we discussed the mapping between concrete and abstract syntax and whether elements of the abstract syntax can be created by different elements from the concrete syntax. This would violate the uniqueness. Second, we discussed the mapping between our DSL and the underlying formalism. We realized the DSL by defining a grammar using Xtext. This grammar maps to the abstract syntax. In order to discuss the uniqueness of this relation, we discuss whether this represents a one-to-one mapping, where every element of the abstract syntax is related to exactly one element from the concrete syntax. Following the mapping approach, elements from the abstract syntax are created by rules denoted in the grammar. Listing 9.1 shows an excerpt from our Xtext grammar. Line 1, 4, and 11 define new rules. These rules determine the concrete syntax. For instance, line 2 defines the concrete syntax of constraints, which starts with the keyword constraint, followed by the constraint's name and its rule, which is defined separately. It's also possible to define inheritance relationships. For instance, line 11 and 12 specify attribute selectors and attribute class selectors as children of data selectors. All these elements are rules of the concrete syntax and are also part of the abstract syntax. Listing 9.1, excerpt from the Xtext grammar, which defines the DSL. The grammar consists of 43 rules in total. 10 of these rules implicate an inheritance relation like data selector and cannot be directly instantiated using the DSL. The abstract syntax contains 42 elements. Each of these refer to exactly one element of the abstract syntax and thus preserve the uniqueness. There is only one exception. In order to enhance the readability, we enable architects to encapsulate parts of the condition using parentheses. Listing 9.2 shows the excerpt from the grammar where the rule is defined. Using the return keyword, we indicate that this rule returns a Boolean operation and does not create an encapsulated logical operation element in the abstract syntax. This represents a threat to the uniqueness because the encapsulation of operation is optional and enables architects to define the same constraints in two different ways. However, allowing the use of parentheses, heißt das so, oder? Parentheses enhance the readability or alter the semantics is commonly among most modern programming languages. As discussed before, uniqueness and expressiveness can become mutually exclusive when followed blindly. In this case, we prefer higher expressiveness. Listing 9.2, excerpt from the grammar which defines encapsulated operations. Next, we discuss the mapping between the DSL and the underlying formalism. Here it's not sufficient to consider the mapping of single elements. Instead, we analyze the semantics of groups of elements and discuss combinations which express similar restrictions. A uniqueness threat occurs when a constraint with identical analysis results can be defined using different elements of the abstract syntax. We exclude the reordering of elements, which does not introduce new features and thus cannot violate uniqueness. In the current version of the DSL, we identify two possible threats to the uniqueness. First, the set of operations which can be used inside a condition part of a constraint is not minimal. Thus, operations can be substituted, which violates their uniqueness. As discussed with question Q2, this is intentional and can be found in most modern programming languages. As stated above, in case of doubt, we prefer expressiveness over uniqueness. The second threat is the concept of characteristic classes. Everything which can be selected by defining and referencing characteristic classes can also be selected directly by utilizing attribute selectors or property selectors, respectively. This is due to the common containment relation to the characteristic type selectors. However, the meaning of both language concepts is different. The use of characteristic classes enables architects to define selections of characteristics independently of their use inside of constraints. As discussed in question Q4, this is motivated by constraints formulated in natural language. Again, we prefer expressiveness over uniqueness. In summary, there are only few concerns regarding uniqueness. All possible threats represent a trade-off decision between expressiveness and uniqueness and have been chosen intentionally. Question Q7. We discuss which knowledge is required to use our DSL compared to using the underlying formalism. Based on the analysis process, we identified 9 different concepts or knowledge categories. Table 9.5 shows which knowledge we consider to be required in order to define constraints in either of both domains. Some knowledge requirements are independent from the choice whether or not the DSL shall be used. This includes basic knowledge on data flow modeling, data-centric Palladio, and the architectural model in use. It's also independent of the approach how much knowledge is needed because the architectural model and its characteristics have to be defined using both approaches. When defining constraints without the DSL, knowledge about the formalism is required. This includes understanding the operation model and the constraint query API. In order to reference elements from the architectural model and its characteristics, architects also have to retrieve information from the transformation trace. Additionally, at least basic knowledge on logic paradigm, the syntax, and common product predicates is required to define constraints in Prolog code. Table 9.5. Required knowledge to define constraints with or without the DSL. Lass mal so kurz stehen. When defining constraints by using the DSL, knowledge on the DSL is required. This includes at least knowing the structure of constraints, the concrete syntax, and common elements. Knowing the internals of the mapping and result mapping or global constants is not required, as well as knowing about the operation model, the transformation trace, or the Prolog language. This is also the case when discussing the map results. They reference the architectural model and its characteristics, and we consider basic knowledge and data flow modeling to be helpful when interpreting constraint violations. This discussion yields several results. First, both approaches require common base knowledge, K1, K2, and K3. Besides the common knowledge, the specific knowledge required to define constraints using Prolog and the DSL is mutually exclusive. This supports the fact that the DSL provides a real abstraction over the underlying formalism. In order to define constraints without the DSL, we count 6 concepts to be relevant. Using the DSL, we only count 4. This indicates that the use of the DSL might simplify the process by requiring less diverse knowledge. Using the DSL hides accidental knowledge because the definition of constraints only depends on essential concepts, for example, knowing about Palladio and the architectural model, and not on transformation artifacts, for example, knowledge about the operation model or the transformation trace. However, it's hard to quantify knowledge. Thus, we cannot prove this assumption without extensive user studies. Immer dasselbe. G3, 933, 33333. Let me free. Space efficiency. The first goal evaluates the language space efficiency. We discuss simple analysis goals with question Q8 and larger analysis with question Q9. Last, we compare the DSL space efficiency compared to constraints formulated in the underlying formalism in question Q10. Question Q8. This question evaluates the space efficiency of simple constraints. Therefore, we discuss the amount of elements in the abstract syntax and the amount of boilerplate code in the concrete syntax of a minimal constraint. This constraint only consists of required elements, namely a rule, a statement, a data selector, and a destination selector. We use an exemplary characteristic type which consists of the literals A and B. Listing 9.3 shows the concrete syntax of the minimal constraint. Listing 9.3, concrete syntax of a minimal constraint. We require architects to name constraints, for example, minimal constraint. The name of a constraint has no effect on an analysis process. However, named constraints are easier to be recognized when reading DSL code from other architects or interpreted mapping or interpreting mapped analysis results. Next, we discuss the keywords of the abstract syntax, namely data, attribute, node, property, and never flows. These vom konkreten Syntax, nicht von der abstrakten Syntax. These keywords are only examples which we chose in order to close the gap between the concrete syntax of the DSL and the constraint formulated in natural language. Still, they introduce some boilerplate code. Attribute and property are used to determine that a constraint selects characteristics. Data and node don't serve this purpose and can only be justified by arguing with readability. This is a conscious trade-off. We consider less and shorter words would benefit the space efficiency not enough to justify the loss of understandability. In order to fully understand the effect of the several keywords, user studies are required. Next, we discuss the abstract syntax. Data selectors and destination selectors are well integrated in our language and serve multiple purposes, for example, selecting characteristics, classes, or nodes by their identity. In the current version of the DSL, rules and statements are less important. Rules have to be contained exactly once in every constraint and are implicitly created in the concrete syntax. Thus, all rules could be moved to constraints without changing the concrete syntax. We justify this decision of rules with the language's expandability. More complex constraints might combine multiple rules using propositional logic in one constraint in future versions of the DSL. This also applies to the statement. In the current version of the DSL, the only possible statement is never flows. However, future versions might support more modalities and flow relations. In order to support this evolution, we kept both rules and statement as part of the abstract syntax. This does not influence the concrete syntax and is not considered to be problematic to architects who write constraints using our DSL. In summary, multiple non-minimal elements can be identified in both abstract and concrete syntax. These elements are motivated by the language's evolution and readability. It's possible to remove these elements from the abstract syntax and shorten the concrete syntax. However, we do not consider the removal of 4 elements in the abstract syntax and 2 keywords in the concrete syntax to be significantly enough to the space efficiency in order to justify verse maintainability and verse understandability. Question Q9. We discuss the verbosity of large constraints and both the vertical composition, adding more elements to a constraint, and the horizontal composition, adding more constraints. First, we define a synthetic constraint which uses most of the provided elements of our DSL. Using all elements, for example, all provided operations, is not considered to represent a realistic scenario. Thus, we select one element of each type, for example, one class selector, one characteristic selector, and so on. This enables us to discuss the vertical composition. Listing 9.4, concrete syntax of large constraints. Of a large constraint. Listing 9.4 shows the concrete syntax of our exemplary large constraint. We use an attribute selector, a characteristic class selector, and a characteristic variable in line 2. Line 3 defines the node identity selector and uses a characteristic set variable. Both variables are used inside a condition together with Boolean operations in line 4. We consider this constraint to be large but still representative for complex analysis goals. First, we discuss the readability. The different parts of the constraints are divided using the uppercase keywords never, flows, and where. Multiple selectors are divided using the AND operator. This shall improve the distinction as well as implicate that multiple selectors are evaluated together. Fehlt das A, aber ich habe es mal hinzugefügt. The readability benefits from the orthogonality discussed in question Q5. Operations in the condition part of the DSL can be nested or combined with operators known from propositional logic. As discussed previously, no final statement is possible on the language readability without the execution of user studies. However, because of the orthogonality discussion, it can be assumed that constraints of different sizes remain readable. This indicates good vertical composition. Second, we consider the horizontal composition of constraints. More complex analysis goals require a definition of multiple constraints. An example is the analysis goal of the UML-SEC secure link scenario presented in subsection 921. We show the constraints using our concrete syntax in listing 9.5. This scenario uses two characteristic classes together with three constraints. All constraints are fairly simple and only consist of one data selector and one destination selector. Listing 9.5, concrete syntax of the UML-SEC secure link constraints. Individual classes and constraints are independent by design. Characteristic classes can only be referenced using characteristic class selectors. Characteristic classes can only be referenced using characteristic class selectors. There is no possibility to reference constraints or to combine them. The orthogonality is preserved. Thus, we propose a good horizontal composition. Question Q10. We compare the DSL space efficiency to the space efficiency of constraints formulated in the underlying formalism. Therefore, we gathered several constraints and used change scenarios already discussed in question Q3. We used the abstract syntax of the DSL in the Prolog meta model. Although we don't discuss the concrete syntax in this question, the evaluation of number of elements using abstract syntax can still be used as indicator. For the discussion of space efficiency of the concrete syntax, please see questions Q8 and Q9. We collected multiple scenarios and constraints. We formulated the constraints using our DSL and using native Prolog code together with the constraint query API. Table 9.6. Number of model elements of scenario constraints. Table 9.6 shows the number of elements of the analyzed constraints. The number of elements used for constraints formulated with our DSL is significantly lower than the number of elements required to formulate the same constraints in Prolog. The range is between 10 times less code, for example for the minimal constraints, and 5 times less code, for example for the large constraint. Taking into account which DSL elements are used to formulate the constraints yields additional results. For instance, the gap between both approaches grows when multiple constraints are defined. We analyzed the UML-SEC secure link constraint in question Q9 when discussing horizontal composition. This is the only evaluated scenario with 3 independent constraints. Because each constraint requires a separate clause in Prolog, the number of model elements grows. The opposite can be observed regarding the vertical composition with synthetic large constraints. Multiple combined selectors require many DSL elements. Prolog benefits from the reuse of predicates and thus scales better. This indicates a better horizontal composition than vertical composition. However, the results provide not enough data for a final judgment. In order to gain additional insights whether or not the usage of selected DSL elements influences the ratio between the number of model elements, we analyze the selected change scenarios from question Q3. We measure the change in the number of model elements for change scenarios S11 to S15, which add different elements to an existing constraint. The result is shown in table 9.7. As shown above, the DSL requires significantly less elements than constraints formulated using Prolog. The ratio between both approaches remain nearly the same for the most of the change scenarios. The only outlier is the addition of a condition with one operation in change scenario S15. Due to the existence of many useful predicates in the list library of Prolog, conditions can be expressed very space efficiently in Prolog. Additionally, our DSL uses characteristic references in order to decouple selectors and conditions, which adds extra elements. This is also indicated by the scenarios which use conditions in table 9.6, namely travel planner, contact SMS manager, and distance tracker. Here, the number of elements when using the DSL is higher compared to the geolocation constraints example, while the number of Prolog elements remain consistent. We discussed the design decision together with the language object analogy in question Q5. Table 9.7, change in number of elements in change scenarios. In summary, the space efficiency of constraints defined in our DSL is better compared to constraints formulated with Prolog code using the constraint query API. The efficiency of different concepts of the DSL differs. Some elements like selectors are very space efficient, while other elements like operations can be reproduced in Prolog with similar space efficiency. The overall ratio between 5 to 10 times less elements Fehler drin. The overall ratio is between 5 to 10 times less elements when using the DSL. (934) G4 Equivalent. Oh Gott. 934 G4 Equivalence of analysis. The fourth goal evaluates the equivalence of the analysis using the DSL compared to the underlying formalism. In question Q11, we evaluate the correctness of the mapping between the DSL and the Prolog code, which uses the constraint query API. Afterwards, we discuss concrete analysis results from constraints formulated both using the DSL and the underlying formalism in question Q12. Question Q11. We perform a correctness proof to validate the preservation of semantics of a DSL mapping. This approach is motivated by the domain of compiler construction. Due to the effort of such formal approaches, we only consider the core part of our DSL, which consists of constraints, rules, data selectors, destination selectors, and characteristic classes. Additionally, we only consider well-formed constraints formulated in our DSL because the DSL mapping is only defined for well-formed constraints. The abstract syntax shows clear restrictions whether or not constraints are well-formed, for example by defined multiplicity. The highest degree of freedom is achieved using the condition part, where arbitrary operations can be nested and combined using propositional logic. Thus, we append a short discussion of the well-formedness of conditions using the lambda calculus in section A1. In the following, we show excerpts of the formalization of our DSL and the DSL mapping prior to performing the structural induction. The complete definitions can be found in section A2. According to the structure of this proof presented in subsection 925, this discussion is structured as follows. First, we formalize the source context and the source language, the target context and the target language using universal algebra. Then, we formalize the transformation between the languages and the source semantics and target semantics. Based on this information, we conduct a structural induction which consists of a proposition, a basis, and the induction step. We start by defining the source context. This contains concepts which we use from data-centric Palladio, characteristics, literals, and elements of the architectural model. We define the domains by enumerating all concepts in a structure as proposed by Jackson and others. Using universal algebra, this can be denoted as follows. A realization of this context can represent a concrete architectural element. For instance, an online shop deploys inside the EU, see section 4.1 for the complete example, can be denoted as follows. This enables us to define arbitrary architectural elements with characteristics and literals, as it's done by the architectural model of data-centric Palladio. We use this structure of the source context domain to formalize the source language, which represents our DSL. We present an excerpt of the structure. We marked several elements with a star, namely data selector, destination selector, and characteristic type selector. As implied by the meta model, these can be replaced by their subtypes using polymorphisms. For instance, every attribute selector is also a data selector. In order to correctly formalize this relation, multiple entries of a structure can be noted. To enhance the readability, we chose to highlight these elements and refer to our abstract syntax for more information on inheritance relations. For the complete formalization of our core DSL, please refer to section A2. Similar to the formalization of the source context and the source language, we formalize excerpts of the target context and the target language. The target context represents both prolog predicates and concepts of the operation model. We denote an excerpt from the structure. Value set types and attribute types are elements from the operation model and represent characteristics. The other entries are synthetical elements of prolog or common predicates. The shown structure is not meant to be comprehensive. It only shows how prolog elements can be formalized using universal algebra. Accordingly, we present an excerpt of the structure which consists of elements of the constraint query API. We discussed this API in section 6.2. Two exemplary elements are Based on these 4 domains, the transformations can be defined. The transformation P maps the source context to the target context, and it's out of scope of this work. It has already been informally defined by Kunz. We only consider the transformation which maps the source language to the target language. This transformation is defined as gamma. In order to discuss the mapping, we give examples for the transformation rules. The first rule maps an attribute selector to a term using the call argument predicate. The characteristic type selector is also specified because a well-formed attribute selector always contains one. The result uses the call argument predicate with 2 terms S and P and a mapped characteristic at C and L. This mapping is part of P and thus not considered here. Please note that we denote the mapped elements C and L using the same symbols as the original based on the work of Jackson and others. Whenever a symbol is reused, its mapping is realized by another transformation rule, which is part of the language transformation or the context transformation. The second rule transformates noch dumm hier. The second rule transforms constraints. The result is a prologue clause which consists of the creation of a list variable S using the unification, its validity check using the stack valid predicate, and a combination of the data selector D and the destination selector Z. Oder Sie, je nachdem, wo auf der Welt wir unterwegs sind. The mapping of these elements is realized using other rules of... Was ist das eigentlich für Tau, oder? Although this mapping uses universal algebra, its structure resembles concrete prologue code as discussed in listing 8.4. The last step prior to the structural induction is the definition of source semantics and target semantics. We show an excerpt from the mapping which maps domain elements to the Boolean values true and false. The definition of semantics of the source language is also based on the source context, for example by referring to architectural elements or characteristics. Additionally, we show an excerpt from the mapping which defines the target semantics. These semantics are based on the semantics defined in natural language by Kunz. Based on the formalization discussed above, we conduct structural induction. We define the proposition of this induction in subsection 925. Hätte hier falsch nachgeschlagen. Furchtbarer Fehler. For every possible model realization R, its meaning defined by the source semantics shall imply the meaning of the transformed result of the realization. Formally, die Formel kennt ihr schon, die habe ich vorhin erklärt. In induction basis, we discuss the implication of meanings of the atomic cases discussed above. Based on the well-formedness, every element in a constraint can rely on the context, which is implied by the surrounding constraint. In the context of the target language T, we assume the existence of a stack S with an operation O on top on which represents the currently selected element. This operation has a parameter P. O is the transformation result of the architectural element, which is derived using the mapping of contexts P. We show the induction basis for 2 examples. First, the transformation of attribute selectors to terms using the call argument predicate. The data flow with literal L of characteristic type C is represented by the parameter P of operation O in call stack S. Ist keine Parodie, ist halt formal. This is inserted by the context and it's the transformation P. The selection of such an architectural element implies its existence on top of the call stack. The parameter P has an attribute C with value L because it's mapped from the original architecture element and its characteristic. Thus, the implication holds. Cool. The second example is the transformation of complete constraints. Any valid data flow is represented by the call stack S in combination with stack valid predicate. The call stack provides the operation O and parameter P, which is the element under consideration by both selectors. Both selectors D and Z in the source languages imply the transformed selectors in the target languages. This is ensured by other parts of the induction basis as discussed above for attribute selectors. In summary, the selected element of the target language is the transformed element of the source language. This is ensured by the context transformation, and the transformation selectors' meanings are implied by the originating selectors. Thus, the implication holds. In the induction step, we show that the proposition holds for more complex examples which rely on the induction basis. This includes the discussion of characteristic type selectors with multiple literals, the use of more than one data selector or destination selector, and the transformation of data selectors to terms using different predicates than call argument, for example, return value or pre-call state. For the sake of brevity, we only present an informal discussion. Characteristic type selectors with more than one literal are mapped by gamma to multiple terms with the same predicate. For example, the multiple call arguments are then combined using products or predicate. The source semantics evaluate to true if at least one of the literals is present. Target semantics of products or predicate evaluates to true if at least one of the selection predicates evaluates to true. This implication holds. The discussion of multiple data selectors and destination selectors is similar. The only difference is that all selectors must be evaluated to true. Thus, gamma uses prologues and predicate. The discussion of different data flow related predicates like return value is based on the definition of data flows. In order to consider each type of flow, such as ingoing and outgoing data of an operation, all predicates are generated implicitly. The use of call states extends mapped constraints by another variable st, but does not change alter. But does not change alter. Ja, war mir nicht sicher. Ja, eins von beiden, nicht beide, ne? Gott, habe ich schon viele Fehler gefunden. But no, it's not alter, finde ich schöner. The underlying meanings. In summary, we formalized parts of our language using universal algebra and conducted a correctness proof using structural induction. The result shows that the semantics are preserved by the transformation, which is performed by the DSL mapping. In this section, we did only explain few examples for the sake of brevity. Und vielleicht auch, weil damals Masterarbeit nur 120 Seiten lang sein durften und ich bereits bei Seite 111 war. A more comprehensive excerpt can be found in section A2, weil Anhang zählt nicht dazu. Question Q12. This question discusses the equivalence of analysis results. We gathered formalized constraints which use the constraint query API from other work and reformulated them using our DSL. This enables us to evaluate whether or not the analysis results are identical. We consider an analysis result identical if the same constraint violations are yielded by the prolog solving process. We hereby ignore the ordering of results. We included 3 different constraints. Ich muss mir noch die Table hier oben vorlesen, ne? Table 9.8, number of found violations in different constraints. Ja. Wo war ich? We included 3 different constraints from the geolocation constraint scenario. We also included a constraint from the travel planner case study. Here we encountered an additional inverted constraint which tests for permitted accesses. Last, we included the UML secure links analysis, which originates from the additional constraints presented in subsection 9.2.1. Table 9.8 shows the results of this evaluation. Most of the resulting constraint violations are found by both the original product constraints and the reformulated constraints. Using our DSL, the analysis did not miss any violations. However, the analysis of the travel planner case study yields 3 additional violations with the use of our DSL. We investigated the reason of this problem and identified that the DSL mapping does not consider 2 predicates of the constraint query API in this context. The use of the operation parameter type and the data type attribute predicate would have avoided the false possible violations. By altering the DSL mapping, this problem can be solved in future versions without changing the DSL's syntax. Based on the metrics of binary classifications, we calculate the precision and recall. Precision, recall. We consider a 100% recall while maintaining a precision of approximately 90% as good result. The remaining false positive results originate from the generalization step prior to the development of the DSL and thus did not become visible throughout the correctness proof, which only analyzes the realized DSL mapping. By fixing this problem, we would approach the equivalence of analysis results. However, strictly speaking, this assumption is only valid for the selected constraints and analyzed part of our DSL. 9.3.5 Summary. We close the discussion of the results with a brief summary of our findings. We evaluated the DSL's expressiveness, usability, and space efficiency. Additionally, we evaluated the equivalence of an analysis of a DSL compared to the underlying formalism. Goal G1 showed overall good expressiveness. In question Q1, we evaluated whether collected scenarios can be expressed using our DSL. 6 of 8 scenarios, or 75%, are expressible. Additionally, we analyzed the coverage of the underlying formalism, namely the constraint query API. Approximately 80% of this API can be expressed either explicitly or implicitly. The result is supported by the evaluation of met requirements which we collected in Chapter 6. 11 of 13 requirements have been realized throughout this thesis. So sum up, oopsie. To sum up, the combination of these results indicates good expressiveness. However, there is still room for more detailed evaluation, for example by collecting more real-world scenarios. With goal G2, we evaluated the language's usability. First, we detected a small reduction in change effort compared to the underlying formalism. We analyzed whether different language concepts are used, which is true for most of them. This yields a good degree of conciseness. We evaluated the language's orthogonality. Due to the structure of constraints which splits up the goal formulation in mostly independent parts, we achieved lower coupling and high orthogonality. In question Q6, we discussed the uniqueness of language features. One threat to the uniqueness is the concept of characteristic classes, which can be justified as trade-off decision between expressiveness and usability. Last, we discuss which knowledge is required in order to use the DSL compared to Prolog code. Besides common knowledge of data flow modeling, the DSL does not require any knowledge about the transformation or the underlying formalism. Moreover, the knowledge required to use the DSL is considered to be less diverse. Goal G3 evaluates the language space efficiency. We considered small analysis defining a minimal constraint in question Q8. We identified multiple elements of the abstract syntax which could be reduced but supports the language's evolution. Additionally, they don't violate the space efficiency of the concrete syntax. We evaluated the horizontal and vertical composition of larger constraints in question Q9. Da ist mir gerade voll die gute Idee für eine Folge While True eingefallen. Warte mal kurz. Okay, sorry. Also falls ihr euch in der nächsten Folge While True fragt, wo kommt denn die Idee her? Minute was weiß ich von diesem Video. Additionally, they don't violate the space efficiency of the concrete syntax. We evaluated the horizontal and vertical composition of larger constraints in question Q9. The overall level of verbosity of our DSL is acceptable. Last, we compared the space efficiency of our DSL with the underlying formalism. The space efficiency of a DSL is better than using the underlying formalism. We measured ratios between 5 and 10 times more required meta-model elements when using the underlying formalism. Last, we evaluated the equivalence of the analysis with goal G4. In order to validate the transformation, we conducted a correctness proof motivated by the domain of compiler construction. We formalized the core of our DSL and performed a structural induction in order to show the correctness of our DSL mapping. Last, we evaluated concrete results of constraints formulated in the underlying formalism compared to reformulated constraints in the DSL. We compared the analysis results and mostly found equivalent analysis results. This yields 100% recall while maintaining 90% correctness due to several false positive violations. 9.4 Threats to Validity. Fred, wo ist er? Komm raus. We discussed the threats to validity of our evaluation. The validity indicates the trustworthiness of the results, to what extent the results are true and not biased by the researcher's subjective point of view. We used the scheme provided by Runeson and others and to discuss internal, external, and construct validity as well as reliability separately. Threats to the internal validity state whether the evaluation results only depends on the investigated factor without interference of a third factor. Overlooking or ignoring additional influences to the results violated the strength of the conclusion. For every unconsidered confounding variable, competing hypotheses arise. In order to evaluate the language's expressiveness, we formulated existing analysis goals using our DSL. We were not able to deformulate 25% of the constraints. This might depend on the language's expressiveness or the author formulation abilities, which represent a threat to the internal validity. However, since the author created the DSL in the first place, the probability of a lack of formulation abilities is negligible. A similar threat occurs whenever we use hand-driven prologue code. This code is used to compare the DSL's abstraction or its space efficiency compared to the underlying formalism. The prologue code is optimized in order to create a fair comparison. Nevertheless, the author's experience of using Prolog is limited. A more experienced Prolog developer might have written better code. However, especially the results of question Q10 are evident, which avoids this threat. Due to the importance of the equivalence of results, we conducted a correctness proof of our mapping. Prior to this proof, the author had near to no experience in correctness proofs. We tried to minimize this threat by discussing our approach with more experienced researchers. However, there is still a risk of faults inside the formalization and structural induction. Threats to the external validity impact the generalization of our evaluation results. In order to evaluate these threats, we discuss whether or not samples are representative for the population. The first threat occurs in question Q3. Here, we discussed the abstraction of a DSL using a set of 15 change scenarios. This selection is not based on a common approach to gather change scenarios of existing models and thus at risk to not being comprehensive enough. The authors were not able to find a common basis for these scenarios in other work and thus selected at their knowledge a comprehensive set of change scenarios. This discussion also applies to our selection of knowledge domains in questions Q7. There is no comprehensive model available to identify these domains. However, this selection is based on the foundations of this work and considers the surrounding process of data-centric Palladio and its required knowledge, which minimizes the risk of missing concepts. Additionally, the discussion does not quantify knowledge and only shows a trend in the required knowledge. Thus, the results are less vulnerable to single missing domains. The biggest threat to external validity is the selection of scenarios and constraints which were used to gather requirements as well as to evaluate the DSL. It cannot be assumed that our selection of 8 scenarios is representative for the domain of data flow modeling. Strictly speaking, our results are only valid for the selected scenarios. In order to cope with this uncertainty, ich habe schon in meiner Masterarbeit von Uncertainty geredet. We try to generalize the GSL's concepts whenever possible. For instance, we included 11 operations which can be used in the condition part of our DSL, although the constraints under consideration only required a subset of them. We discussed the comprehensibility of this selection in question Q2. Still, this threat affects the DSL and all questions which depend on the selection of constraints, for example the discussion of expressiveness and conciseness, as well as the equivalence of analysis results. Threats to the construct validity. State whether our selection of questions and measurements contribute to the overreaching goals. To minimize this threat, we included the results of other works on the development of DSLs into our process. The usage of a goal question metric plan does also mitigate this threat. We consider our plan to be sufficient to evaluate our approach. Still, some attributes cannot be evaluated without considering the user's behavior. Due to the high effort, we were not able to perform user studies in the scope of this thesis. Reliability deals with the repeatability of the evaluation and asks to what extent the data and the analysis are dependent on the specific researchers. In order to aid the repeatability, we defined the evaluation design in section 9.2 prior to discussion of the results. Additionally, we publish our prototypical implementation along with models and constraints created throughout this thesis to allow others to reproduce the evaluation. Und falls ihr euch also gerade eben gefragt habt, hat er nicht gerade eben in Threats to Validity einfach mal alles kaputt gemacht, was er in der Evaluation gemacht hat, indem er einfach überall was Negatives gefunden hat, überall ein Haar in der Suppe und die ganze Zeit nur über seine eigene Evaluation gemeckert hat, wo die kaputt diskutiert und verwundbar wäre? Die Antwort ist ja. Denn das ist Wissenschaft. Du stellst eine These auf, du versuchst sie zu belegen, aber du versuchst sie auch zu widerlegen. Und ja, das habe ich hier gemacht. Und jetzt gehen wir noch einen Schritt weiter und jetzt widerlegen wir nicht nur meine Evaluation, sondern den gesamten Ansatz. 9.5 Assumptions and Limitations. In this section, we discuss assumptions we made during the design and realization of our DSL. This includes analyzing the limitations of the current version of our approach. First, we assume our selection of scenarios and constraints to be sufficient representative for the domain of data flow modeling. We already discussed this concern together with the external validity in section 9.4. This also influences the design of our DSL. We tried to generalize our approach but still depend on the scenarios we found during the initial research. Another assumption affects the analysis of data flows using the constraint query API of data-centric Palladio. The operation model uses call arguments, return values, and call states to represent data flow going in or out of operations. In order to cover all possible flows, our DSL model combines all predicates, call argument, return value, pre-call state, and post-call state. Here, two problems occur. In theory, it's possible to identify a constraint violation in ingoing call data as call argument as well as in outgoing data as return value. This would yield two constraint violations which belong to the same problem. Furthermore, it depends on the architectural model whether these different types are used. For instance, if a transformed architecture does not use call arguments and return values at all, the analysis becomes unnecessary and might even yield execution errors if these predicates are not generated at all. This could be solved by coupling the transformation of the DSL and the architectural model. For the initial design, we ignored this detail and always considered all four data flow related predicates as discussed above. The first limitation is related to Palladio. Using node identity selectors, architects can select elements from the architectural model by specifying the assembly context, a component, and a Ceph. However, this integration is not complete. For instance, nested assembly contexts are not supported. The second limitation occurs from the structure. Wie konnte denn der nicht auffallen? From the structure of constraints in our DSL. We defined a fixed structure of a selection of data and data flow destinations. Constraints which do not match the structure cannot be expressed. This is related to the third limitation. Because we do not meet requirement R9, our DSL is not capable of considering multiple data flows in one constraint. Data availability 9.6. Data of this thesis is publicly available. This includes the prototypical implementation of our DSL, its mapping, and the result mapping along with models and constraints collected and created during this thesis. Chapter 10. Conclusion. To conclude this thesis, we summarize our approach and findings in section 10.1. We give an outlook on future work in section 10.2 and express our acknowledgements in section 10.3. 10.1. Summary. The goal of this thesis was to provide an approach to formulate analysis goals for data-driven design time analysis. In order to abstract from the underlying formalism, we propose to use a domain-specific language, DSL, which uses the terminology known from the domain of data flow modeling. We provided a mapping between the DSL and the formalism which is used for the analysis. In order to ease the interpretation of analysis results, we defined a mapping of results back into the architectural domain. Our research questions targeted the collection of architecture-level constructs to define data flow constraints and the mapping of constraints and results between the architecture and the formalism. Our DSL is based on the collection of data flow scenarios and constraints from other work. We derived requirements from real-world use cases and combined this information with analysis capabilities of the underlying formalism, which is given by data-centric Palladio. We generalized the analysis goals of multiple scenarios and defined the syntax of our DSL. Using our DSL, architects are able to describe data flow constraints by specifying data and data flow destinations using characteristics. The expressiveness of the selection is enhanced by the definition of conditions on variable characteristics as well as the definition of characteristic patterns using characteristic classes. We defined a mapping from our DSL to the underlying formalism. This transformation generates executable Prolog code which uses the Prolog API provided by data-centric Palladio. Together with the existing transformation of architectural models to Prolog code, our mapped constraints can be evaluated by the Prolog environment. Afterwards, our result mapping transforms identified constraint violations back into the architectural domain and presents them to the architect. Our approach enables architects to specify data flow constraints while modeling the architecture without the need of switching the abstraction level. The transformation to and from the underlying formalism is fully automated. Thus, architects are not required to know how to use the underlying formalism. Only basic knowledge on data flow modeling, data-centric Palladio, and our DSL is required. We evaluated our approach regarding the DSL's expressiveness, usability, and space efficiency. In order to evaluate the expressiveness, we collected scenarios and case studies from other work and reformulated the constraints. 75% of all considered constraints can be expressed using our DSL, which matches the coverage of the API of data-centric Palladio, which is 80%. Regarding the DSL's usability, we considered the abstraction from the underlying formalism, the language's conciseness, orthogonality, and the uniqueness of features. Overall, the results look promising. Our DSL requires less effort to define and alter data flow constraints than the underlying formalism. All concerns regarding other language quality attributes originate from trade-off decisions regarding its expressiveness. The evaluation of the DSL's space efficiency indicates that the DSL requires 5 to 10 times less code than similar constraints defined using the underlying formalism. Additionally, we evaluated the equivalence of the analysis using our DSL to define constraints compared to the underlying formalism. We performed a correctness proof of the mapping of the core DSL. We also evaluated whether the analysis results of constraints defined in our DSL match the results of already formulated constraints in Prolog. The results show a recall of 100% while maintaining 90% precision. This thesis is aimed to improve the understanding of the definition of analysis goals for design time analysis, which bridge the gap between the architectural domain and the underlying formalism. We developed and realized a DSL and its mapping, which improves the architect's capabilities by removing accidental complexity. We also discuss requirements which have to be considered in order to enable the mapping of analysis results. 10.2 Future work. The approach presented in this thesis is ready to be used in its current form. However, we discovered several parts which can be enhanced and are thus subject to future work. First, we identified several smaller improvements of the current version of the DSL. Currently, constraints always consist of exactly one rule, which restricts the flow of data to one destination. Here, supporting multiple routes could be combined using propositional logic, which would enhance the architect's capabilities. Another placeholder element of our DSL is the statement, which currently always restricts data to never flow. Here, more modalities would be possible, for example requiring data to always flow or to flow at least once. This discussion is based on model logic, and the underlying formalism is already capable of analyzing constraints of such nature. Moreover, the DSL could be extended to support types of constraints which do not follow the pattern of selecting data which flows to a selected destination. An example is the consideration of multiple data flows, for example, that are not allowed to be joined in a selected node. This requirement is motivated by a real-world scenario analyzed in this thesis. Another type of constraint is the specification of data without considering its destination. For example, requiring certain characteristics to never appear in a datum during the analysis. In the current version of the DSL, architects can choose the target model type. Currently supported are constraints based on data-centric Palladio and its underlying operation model. However, the genericness of the DSL might suffice to support more than these two data flow models. Further research is required to collect more data flow modeling environments and generalize the analysis goal formulation. Last, the quality of existing DSL could be enhanced by executing a user study. This would not only help to improve on the concrete syntax and usability of the language, but also yield empirical results whether the usage of an abstraction approach like a DSL improves the architect's capabilities and performance while defining data flow constraints. 10.3 Acknowledgements. I want to thank my advisors Stefan Seifermann and Frederik Reiche for their support, which greatly improved the quality of this thesis. I also want to thank Dr. Thomas Kühn for his advice on the realization of formal correctness proofs. Last, I want to thank all participants of the breakout group Evaluation of DSLs during the research retreat in March 2020 for their great input. Appendix. In the appendix, we present additional information which completes this thesis. In section A1, we discuss the well-formedness of conditions, a part of constraints in our DSL. We show a more comprehensive formalization of the part of the correctness proof in section A2. In section A3, we show complete examples of generated prologue using our DSL mapping. Last, we present a complete meta model in section A4. A1. Well-formedness of conditions. The well-formedness of constraints formulated in our DSL is ensured by the abstract syntax to a large extent. The highest degree of freedom exists in the condition part, where architects can freely nest and combine operations on characteristic variables. See section 7.4 for all details. We chose a strictly functional approach without side effects or states. In order to discuss the well-formedness of conditions, we formulate these operations using the lambda calculus. This discussion is part of the appendix because it's not considered to match the evaluation, but instead provides a different view on the definition of conditions. Listing A1 shows several examples of conditions. For instance, the test for emptiness and the intersection of two set variables in line 3, or the comparison of variables in line 4. Line 5 shows how these operations can be nested in order to formulate more complex conditions. Listing A1, examples for conditions which consist of multiple operations. Operations can be expressed using the simply typed lambda calculus and three types. Characteristic variable, short var, characteristic set variable, short set, and Boolean variable, short bool. Translated operations can be denoted as follows. We use this formalization to show the relation between the strictly functional conditions and the type system of the simply typed lambda calculus. Cardelli uses a formal language to define type system. A type system is a set of judgments which represent assertions. A judgment can be valid or invalid. The typing environment holding three variables is denoted as follows. Our abstract syntax implies that the most outer operation is always a Boolean operation. This assertion, the type of a well-typed condition is always bool, can be formalized as follows. Based on the concept of judgment, this type system of the simply typed lambda calculus can be defined with the following rules: tvar,tabs, and tapp. Grüße gehen raus an Programmierparadigmen. The first rule, A1, handles three variables in a typing environment and is used to extract a variable x of type A, which can then be used in a term. The second rule, A2, gives a term a function type if its body is typed correctly. The third rule, A3, applies a function m to an argument n. Based on these foundations, we can verify terms using the formalized operations and the simply typed lambda calculus type system. The typing environment contains all free variables and all translated operations as shown above. This can be denoted as follows. To demonstrate this, we show the type derivation of two terms which use the isEmpty operation. First, we use a characteristic set variable s. This is typed correctly. Second, we use a characteristic variable v, which is not typed correctly because a single variable cannot be empty. Thus, isEmpty is only defined on set variables. This can also be seen in the formalization of the operation shown above, which defines isEmpty as lambda expression from set to bool. The derivation tree for the correctly typed term isEmpty s, with s being a characteristic set variable, looks as follows. Ja, da gibt es extra ein LaTeX-Paket für. Starting at the bottom of the derivation, we first split the term isEmpty s into the operation isEmpty x and the variable s, on which is applied using the tapp rule. This variable is a free variable and thus part of the typing environment, which is verified using the tvar rule. The isEmpty x operation is further split into its argument and the atomic operation using the tapps and the tapp rules. Last, the existence of the operation in the typing environment is verified using the tvar rule. In this derivation, every judgment succeeds until no further rules can be applied. Thus, the term is typed correctly. Next, we consider the derivation tree of an incorrectly typed term isEmpty v, with v being a characteristic variable. The structure of this tree is similar to the example discussed before. However, the application of the tapp rule, a variable of type set, is expected because the operation isEmpty x is defined with the function type set to bool. Thus, the tvar rule tries to find a variable v of type set in the typing environment, which fails because v has a type var. Thus, not every applicable judgment succeeds and a type error occurs. These two simple examples show how the simply typed lambda calculus can be used to express and verify conditions. This approach is applicable to terms of arbitrary size and nesting based on the three judgments presented above. Thus, we consider conditions which follow our abstract syntax to be type safe. A2. Correctness evaluation. As part of our goal G4, which considers the equivalence of analysis results, we outlined a correctness proof with question Q11 in subsection 925. In the results discussion in subsection 934, we presented only short excerpts of the formalization for the sake of brevity. In this section, we show more comprehensive examples. We present concepts of the source context, the source language, the target context and the target language. Then we show the formalization of the transformation as well as the semantics. Last, we present more examples of the induction basis and part of the structural induction. Please note that the formalization shown in this section is still not exhaustive and has only been performed for a subset required for the structural induction. A.3. Mapped prologue code examples. In section 8.6, we discussed the transformation of two exemplary scenarios, the geolocation constraint scenario and the access control scenario. For the sake of brevity, we only present excerpts from the generated prologue code using the DSL mapping. In this section, we show the complete generated code for both examples. Listing A2 shortened concrete syntax of constraints of both exemplary scenarios. Listing A2 repeats the constraints of both scenarios. The first constraint in line 5 to 7 and the characteristic class in line 1 to 3 belong to the geolocation constraint scenario. The second constraint in line 9 to 13 belongs to the access control scenario. We show the generated code of the geolocation constraint scenario in listing A3 and the code of the access control scenario in listing A4. Listing A3, complete transformation result of the geolocation constraint scenario. Listing A4, complete transformation result of the access control scenario. A4, meta model. We present the complete abstract syntax of our meta model in figure A.1. In order to enhance the readability, we omit attributes and the relations between operations and references. For more information, please see Chapter 7. Figure A1, complete abstract syntax of the meta model of our DSL.